Hey everyone! So I've put together a 3-hour workshop that will teach you how to build a Telegram bot agent. I will start with a 1-hour LangGraph crash course, and then I will move into a set of coding sessions. These coding sessions will teach you everything you need to know about how to implement STT systems, speech-to-text, TTS systems, text-to-speech, image generation modules, and also vision language models, VLMs. You have all the slides and all the code available to download from my Substack article, and by the way, you have the link in the description below. So feel free to pause the video now, grab those resources, and come back so we can dive right in. If you're ready, let's get into it. What's up? So just before we begin with these 3 hours hands-on learning, I just wanted to give you some quick instructions about how to download the code and the slides for this workshop. So I will leave in the video description a link to this Substack article in my Substack publication in the Neural Maze. And in here, you just need to scroll down. I'm just talking about the intuition behind this workshop and also why I wanted to do it this way. By the way, the workshop is split into 2 parts. So today I'm launching this first part for free, that it will contain a lot of things, as you will see. It's 3 hours of video. And the second part, which will be released on October the 15th, will add all the production deployment. Okay, we will add observability, we will turn notebooks into the robust Python application, the fundamentals of LLMOps, and finally how to deploy everything on Amazon using AWS Lambda functions. But this is exclusively for premiums. You can go to here to this subscription plan, and if you're interested in the things that I will be launching next week, you can just go here and choose the monthly or the annual premium tier. Okay. All right. So about how to get started with part 1. So the first thing we need to do is to download the slides. You can go to this section and just download the slides using this button. For getting the code, it's basically the same, but you just need to go here. In fact, if I click this button, this is a shared drive, and this is the place where I have put all the different Google Colabs that I will be running throughout the workshop, right? There is a total of 7, I think. No, it's 8 different collabs. Okay, perfect. And finally, you will see here this watch the video, which is empty right now because this video that I'm recording will be placed in here for my Substack subscribers. But yeah, this is everything for these instructions. So I know you're very excited to get started with all of this. So yeah, let's get into it and hope you have a very nice workshop. Bye-bye. What's up, builders? Welcome to this workshop. Welcome to this online version of the workshop that I gave in Bengaluru. It has a few changes, but 99% of it is going to be the same. Of course, I won't have the privilege of having each one of you in front of me, but maybe next time. So yeah, let's get started. All right, so first of all, let's start with the basics with describing the project. And in this workshop, we are building a multimodal Telegram agent from the ground up, from scratch. We will explore how to use LangGraph to create agentic workflows. You can see by the name of this workshop that is going to be specific to LangGraph. Maybe in future workshops, in future courses, we can touch any other agentic framework like RuAI, Pydantic AI, etc. But today it's going to be about LangGraph. We will rely on OpenAI models to handle text, audio, and image messages. For long-term memory, we are going to use Chroma, and to give our agent a distinct voice, we will bring in ElevelLabs. The only thing in which you will need to pay some money is for OpenAI, all right? But LangGraph is free, ChromaDB is also free, And in Level Labs, in case you are you haven't exhausted the free tokens, you will be able to run the trials that we are going to use with the free tier. So yeah, by the end, we will create something like this screenshot that you can see in here. I called my bot Karen, which is a senior machine learning engineer from Bengaluru. Of course, I wanted to be as close as possible to the workshop in Bangalore. And that's the reason why I kept Karen. If some of the viewers were in that workshop, maybe this brings some good memories. All right, so yeah, let's keep going. Now let's do a bit of a deep dive into the project. Before, I just gave you an overview of what we are going to build, and now we are going to see how the system is going to be built. All right, so the system that you can see on the right is built of 7 major components. First of all, we have this agent workflow that you can see in this screen that I'm highlighting. This agent workflow is the main goal of LangGraph, and it's built upon this LangGraph graph builder, a set of chains, a summary, chat history, etc. Then we have the agent memory, which, as you might recall, we have 2 types, the long-term memory and the short-term memory. The short-term memory is going to be implemented using SQLite. This is very similar to the ABA project that I built like 6 months ago, but it's an easier version, not so complex. And then from the long-term memory, we are using ChromaDB. All right. As for the third component, I'm just going to focus on STT, on speech-to-text module. The fourth component is the TTS, the text-to-speech module. Then we have image understanding, image generation, and finally the Telegram bot, which if you have done the ABA course, you will see that building a bot using Telegram is a much simpler task than building the same using WhatsApp. All right, let's keep going. So the project is structured in 2 parts, and this is very important because what you will see today is just the first part, the free part of this project. It's going to be deployed on October the 8th. Of course, today is not October the 8th. It's covered in this, it's basically all the content that we are going to cover in this workshop. The code and the video are free. You're going to have access to it through my Substack article. And finally, it's based on Colab notebooks. So all the code is going to be, all the code that we are going to work with in this workshop is going to be hosted in Google Colab. For the second part, things are getting much more interesting, but this is just for premium subscribers in my Substack account. This is going to be live on October the 15th. That's next Wednesday. This is not covered in today's video and article. And in this second part, we're going to implement the full application. And the full application means that we are going to take all of the system and we are going to turn it into a fully fledged application, production ready, and that is going to be deployed using CI/CD to AWS. All right. By the end of this video, I will give you a hint of what we are going to build, but it involves some LLM ops, CI/CD pipelines, and also Amazon Lambda functions. That's the place where we are going to deploy the system. And yeah, I think it's going to be really cool. But as I was saying, this is just for premium subscribers. So both the code and also the video just going to be accessed if you subscribe to the premium tier in my Substack. All right, so let's get started then. We have now covered the basics of the project. Now it's time to start with the theory before we delve into the practice. So before we begin, this is something that if you've been subscribing to the Neural Maze, both YouTube, Substack, LinkedIn, etc., I bet you already know what is an agent. But since I don't know the exact starting point of many of the viewers of this video, I just wanted to explain in 5 minutes what an agent is. All right. And to do that, I'm just going to take this diagram. By the way, this diagram belongs to one of my first article. I think it's the first article of the publication. So yeah, I have very good memories about this. This is the way in which I really like showcasing what an agent is. And for me, an agent is built of 4 components. First, we have the LLM. You can understand this LLM as the agent's brain, and you can see it in here inside the circle. Then we have the planning component that's composed of different prompting techniques that you can use to improve the planning, like tree of thoughts. And you can see here inside this rectangle, tree of thoughts, chain of thoughts, etc. And then also the workflows. You can also implement workflows, like for example, the React technique, which is a workflow in which we have 3 different components, a loop of reasoning. So that's something that you can achieve with workflows, and that's something that we are going to see today, because in LangGraph it's very easy to implement this React loop. Then we have the memory, which we can split into a short-term memory and a long-term memory component. In here, for the short-term memory, you can understand this as the attention window of your LLM, all right? All the different information that is going to be considered whenever you generate a response. And then we have the long-term. Long-term, here I'm just mentioning and just showing 3 vector databases that you can use, like Quadrant, ChromaDB. This is my pick for today's video. And also MongoDB. You're probably aware that MongoDB is not exactly a vector database, but it also offers some good functionalities for this. And finally, we have the tooling, external resources or actions an agent can use. Here in the original diagram, I was just putting this connection with a set of tools, a Wikipedia tool, YouTube tool, Google search tool, etc. Now I've also added this tiny icon in here. You're probably aware of what this is, right? This is for MCP, for the Model Context Protocol. And the thing is that it seems at least that we are the presence of one of the first standards when designing agents and when designing how agents interact with tools, and that's probably this MCP protocol, all right? And that's the reason why I also added here. Of course, you can access all of these tools without MCP, but it's more and more advisable to use this protocol whenever you want to interact with a tool. All right, so that's basically everything that I wanted to say about agents. Remember, agents are just built of 4 components: an LLM, a planning component, a memory component, and the tools component. So now that we understand what an agent is, it is time to start my crash course on LangGraph, which is the first step or the first building block of today's workshop. But before I begin with LangGraph, let me give you a quick glimpse of the 6 levels of autonomy as defined by Harrison Chase, the CEO of LangGraph, because I think it's really, really interesting. So according to Harrison Chase, there are 6 levels of autonomy in LLM applications. We have the code level, the LLM call level, the chain, router, state machine, and autonomous. And in this diagram that I've built, you can see the degree of autonomy of each level. Code is 0 autonomy, so in the code, the desired output of step is human-based. Humans need to decide which steps to take, and humans as well need to decide what steps are available to take. If we go to the LLM call, you can see that the LLM is going to decide the output, all right? But both humans are in charge of decide which steps to take and decide what steps are available to take. For the chain, it's basically the same as before for the LLM, but we are adding multiple steps, because remember that chains, that's something that we are going to cover in future slides, but chains are just a sequence of different LLM calls or other operations. If we keep scrolling down, you will see this router level, and the router, the LLM, is in charge of deciding the output of steps, and it's also in charge of deciding which steps to take. This is something that, as well, we are going to implement in today's workshop. The only thing is that for the router, humans are still in charge of deciding what steps are available to take, all right? And if we keep scrolling down, the state machine is almost the same as the router, but there are cycles available inside the LangGraph workflow, inside the workflow in general. And then we have the last level, which is the goal of all this explosion of agents, which is the autonomous agent. And this agent is going to decide the output of each step. It's going to decide which steps to take, and it's going to decide what steps are available to take. All right. Today's video, I'm not going to create an autonomous agent. We're just going to create a state machine. All right. Because the agent, this Telegram bot agent, is going to decide the output of each step, is going to decide which steps to take. We are going to implement some cycles as well, because there's going to be a React loop implementation. But this agent is not in charge of deciding what steps are available to take. All right, so I'm defining all of these steps, and that's the reason why I've labeled this Telegram bot agent as a state machine agent. All right, but yeah, that's just a matter of definition, to be honest. If it manages to solve your use case, then don't really mind about labeling your stuff. All right. Okay, so I'm just going to skip through this a bit more quickly. So the first level, as I was saying, is not even an LLM application. It's just traditional code. The second level is reduced to single LLM calls. Remember the second level, and it's not bad, but of course it's fairly limited. You have start, this LLM node, and then an end. Okay, you have an input, a prompt, and the LLM generates some output. Of course, you can attach tools to this LLM. This LLM is not constrained to be just a single call. It might use some tools to generate a response, etc. Then we have the third level, which introduces chains, as I was mentioning before, and that was the original goal of LangChain. And chains are a set of steps defining a control flow. You can see here that we can start with an input prompt, and then there are a set of steps, and in the middle, an LLM call. And this is what we refer to as a chain, and it generates an output. Then we have the fourth level, which introduces the router pattern. This is probably the level that I use the most in many of my projects. And the thing is that the LLM is in charge of picking their own control flow. So the LLM in here, after step 1, is going to decide, should I go to step 2 or should I go to step 3? All right, the LLM is in charge of taking this decision. Perfect. So now for higher levels, 5th and 6th point in the direction of semi-autonomous, that's the state machine, or fully autonomous agents. All right, and here you can see how the fully autonomous work. And for our Telegram agent, we need to find a trade-off between flexibility and reliability. And that's the reason why I've chosen LangGraph, because it will become really handy as it helps us bend the reliability curve. And what do I mean by this? So the thing is that if you start adding more autonomy to these agents, the reliability is going to decrease, all right? If you take a look at these diagrams in here, you will see that as the agency increases, this green line, the reliability is going to decrease. What's the advantage of LangGraph? That it makes the curve steeper, all right? So the decrease in the reliability is not as profound, it's not as steep as if we were not using LangGraph, all right? That's the reason why I've chosen this framework, because I think it's one of the best picks, if not the best, in my opinion, for any agent-related topics. All right, so I've been talking about LangGraph, and you probably know LangGraph if you've been following this channel and this Substack. But let me give you a proper introduction to LangGraph, because I've always taken for granted that you already know this framework, but maybe it's not the case. So I just want to give like 3 basic characteristics of this framework. So first of all, LangGraph is a framework designed for building complex stateful LLM agents and multi-agent applications. All right. Keep in mind this stateful stuff because it's important. Because LangGraph is going to treat all the agentic workflows, all your agentic systems, as graphs, as the name implies, LangGraph. But these graphs have a state attached, and that's the reason why in the canonical definition of LangGraph, they are adding this stateful word, all right? LangGraph, as I was saying, uses a graph-based architecture that gives developers fine-grained control over agent behavior, and is ideal, as I said before, for creating robust, production-ready AI systems that require precision and adaptability. Okay. I can assure you that it's a bit arid in terms of theory, but we are going to get to the code in just one slide. So LangGraph models agent workflows as graphs, as I said before, and using three main components. Component one is the state. Remember that LangGraph modules the agentic systems, the agentic workflows as graphs, and these graphs need to have a state attached. This state is a shared data structure that tracks the current status of your app, your workflow. Here you can see an example of a workflow. This is from ABBA, one of the courses that I've done for the neural maze, but today we are going to build something really similar. Then we have the nodes. This is another entity, another of the three main components. Python functions that define the agent behavior. They take in the current state, perform some actions, and return the updated state. There's something here that I want to mention, and is that you don't need to have an LLM call inside each one of the nodes. Nodes could be a simple, plain Python function, like deterministic, traditional Python function. And finally, we have the edges. Python functions that decide which node runs next based on the state, allowing for conditional or fixed transitions. So we have a set of nodes, and we have different connections that connect the nodes to each other. And these edges could be something really straightforward, like one link that links together node 1 and node B, but it could also be some Python functions that you can attach to the edge. And finally, apart from the nodes and the edges, this is like a simple graph, we also need to add the state. And that's the reason why we talk about complex, stateful agentic applications, so complex, stateful agentic workflows. Okay, there has to be a state that keeps track of the status of your app, of your workflow. Perfect. So it's time for the funny part. This is our first coding session, by the way, something that I missed at the beginning of the video. So there are a total of 7 notebooks for this workshop. And whenever you need to open the notebook, I will create a slide like this one, all right? And I will tell you that it's time for a coding session, and I will just I will just specify the specific notebook that you need to open. In this case, we just need to open this _LangGraph crash course, all right? That you can find, of course, in the same Google Drive that I've shared with you. Perfect. So I have it in here, LangGraph crash course. Let me connect to the, first of all, to the machine. And now this is going to be a pretty decent one, like a long one, but I hope by the end you have an overview of what LangGraph is and the different implementations that you can achieve with LangGraph. In a nutshell, we are going to implement more or less the different levels that I've talked to you about a few minutes before, all right? We are not going to do that for the autonomous system. We are just going to stop at the state machine, because the state machine is enough for the kind of project that we want to build today, all right? So I don't want to spoil the surprises, so let me, okay, I think now you can see much better the screen. Let's start with this LangGraph crash course, because I'm talking too much. So yeah, this is just the definition, basically what you have seen in the slides before. We're just going to install LangChain OpenAI. This is necessary if you want to interact with chat models from OpenAI, LangChain Core, LangChain Community, and LangGraph. All right. So the first section is about understanding LangGraph structure. Remember, we have three components: nodes, edges, and a state. So let's start with the state. So this schema, this state schema, acts as the input structure for all nodes and edges within the graph. And even if I'm 100% sure that you know that this is not the proper way to do it nowadays, because you have classes that already implement all these type dictionaries, I wanted to start with the basics of how would you create an state from scratch. If you were just beginning in LangGraph, you knew nothing about different helper classes that they have implemented, how can I create a state for my graph? And the class, the type of your state is typed dict. You just need to import from typing extensions this type dict class, and you just want to inherit from this class, okay? Just creating this new state. The state has to be attached with different properties that you can add to your state. In this case, I'm just going to create this graph state, which is a string, okay? But you could be adding multiple things like messages, which is a list of strings, and you can do the same with audio, which is bytes. This is exactly what we are going to do when we start making our system way more complex, and by the end of this workshop, you will see that our state is going to be much bigger. But yeah, just to keep things simple, since we are starting, let's create, first of all, this state. Let me have, that's it. And yeah, let's keep scrolling down. So now that we have our state called state, just keep evolving, and let's take a look at the nodes. So nodes, as I mentioned before, are just simply Python functions, and each node takes the state as its first positional argument based on the previously defined type dict. Translated into human language, each node is going to take the state and is going to return an updated state, all right? Since our state includes the graph state, then each node is able to access the properties of this state, but we only have this graph state as property, so we just need to modify this state graph state. All right, and here I just put this hint, this node, just so you remember this, that each node returns an updated value for graph state, and by default, this new value will overwrite the existing one in the state, right? Okay, so this is probably the most stupid application you can build on LangGraph, but bear with me. So we are defining three nodes. Node 1, remember, it receives a state, so node 1 is going to print some random comment here, I'm node 1, and it's going to return this graph state, okay, this dictionary containing the property that we want to modify. And this property, graph state, is going to be modified by adding to the original value of the graph state with a welcome. All right, remember that by default, this state is going to be an empty dictionary, an empty string, sorry. The graph state is going to be empty. All right, so node 2 is basically the same. And in here, instead of adding welcome, we are adding to the Data Hut Summit. Just here, another Easter egg for the Data Hut Summit workshop, what I gave this workshop. And finally, this node 3, we're just going to add to Bengaluru, another Easter egg. All right. Perfect. So now that we have the three nodes defined, it's time to go with the last part, with the edges. And edges are of two classes. We have normal edges and we have conditional edges. Normal edges are used when you always want to transition from one node to the other, so are just like graph edges, like single edges. For example, from node 1, go to node 2. And conditional edges allowed for this dynamic routing. So based on some of the dynamic computations inside this edge, the edge is going to connect to either node 1 or node 2. Okay, that's something that we are also going to see. And in fact, the next cell is just going to implement this conditional edge. Okay, the site node is a conditional edge. It's going to accept as input the state of the graph, and it's just going to return one of these, either node 2 or node 3. As user input, we just take in the graph state. Remember, that was the property that we defined for our state. And then, based on this random computation, you're going to return either node 2 or node 3. You can see here it is basically the flip of a coin. So depending on a 50% probability, we are just returning one or the other. Perfect. So we think we have already run this cell. Now we have the three entities that take part at any workflow: states, edges, and nodes. It's time to build the graph, to build properly the workflow. All right. So first, we are just going to initialize this builder. This is the entity or the object that you need to use to explicitly add the nodes, add the edges, and also to compile, to create the graph. And we are also going to introduce two very important, I would call it pseudo nodes or meta nodes, because they are not properly nodes. They are just here to design the start and the end of your workflow. All right. So here you can see, some helper functions to display the graph. And then from LangGraph.graph, we are importing this state graph, which is necessary to create the graph entity, the graph object, and also start and end to design the start and the end of this workflow, right? First of all, we are just going to define the nodes. So we are just adding, using this add node, the function that we defined before for the node with a label, with a name. In this case, I just want to be a bit coherent. So if I name the function node_1, then the label is going to be the same. All right. And the same goes for node 2 and node 3. After that, we are just defining the edges. All right. And this is interesting because we are not just adding, okay, node 1 is going to be connected to node 2 and node 2 to node 3. Imagine. No, we are starting with the start node, with this meta node that we need to use whenever we want to tell LangGraph, okay, this is the place where the workflow is going to start. So that's the reason why we need to use this start and connect this start node with the node 1. Then we are adding this conditional edge that is going to connect node 1 with either node 2 and node 3. How? By following the logic that we implemented in the decide node. All right, that's the reason why we need to add this decide node function to the conditional edge call. And finally, just add the edge that connects node 2 to the end and node 3 to the end. If you miss one of these, LangGraph is going to complain because there's no way for LangGraph to understand where or when this workflow is going to end. So that's the reason why you need to connect every missing links to the end nodes. Then we are just compiling the graph with this builder.compile. And finally, this is not necessary, but it's a way to display an image like this one. All right, so let's run this cell. And now just execute the graph. So one important thing, I mean, you don't need to be to go very deep into this. Of course, if you want to contribute to LangGraph or even to have just a deeper understanding of what's happening under the hood, I just wanted to give you a hint of what's happening in here. So the moment we compile the graph, this graph object that we have generated when we run the compile method implements or conforms to the runnable protocol. This runnable protocol is also shared by tool objects, is also shared by chat models. Everything in LangChain, or almost everything, is sharing the same runnable protocol. And that's the reason why you have interfaces, you have implementation, to functions like invoke. If you've been using LangChain or LangGraph, I bet you've used this dot invoke multiple times, or dot asynchronous invoke, or any of these methods that are actually implemented in this runnable protocol. So whenever you inherit from this interface, you need to implement these methods. And that's something that also happens for this graph object. Perfect. So now that we know it, just invoke the graph. Of course, we need to pass the input message. And this input message is just this, hi there, it's Miguel. This is the first, the first state that the graph is going to receive, all right? The starting state is just, hi there, it's Miguel. And of course, we are just going to add to this state, this welcome to the Data Hub Summit or welcome to Bengaluru, depending on the result of this, the side node, depending on the probability. Nice. So if I run first time this, you will see that, hi there, it's Miguel, welcome to Bengaluru is the output. If I keep running this, eventually it will change. You can see in here that now, hi there, it's Miguel, welcome to the Data Hub Summit. So in this particular execution, node 1 and node 2 are being triggered. If I keep running this, there will be a time in which node 3 is the one to be invoked. So yeah, seems probability is chasing me. Okay, here, node 1 and node 3. So you can see right now that probability flipped to the other side, and now two different nodes are being triggered. All right, so now that we have a general idea of how LangGraph works, it's time to see how LLM applications can be implemented using this framework. All right, so remember this. This is the original, the image from Harrison Chase article, and remember that there was six levels of autonomy, right? From code to autonomous agents. So now we're just going to keep implementing each one of them, right? Not each one of them, to be precise, because, for example, LLM calls is something that we are all aware, but we are going to start by implementing chains, then also routers, and then adding cycles to our workflows. Here, there's also an important remark. Our Telegram agent will follow a pattern known as the router, in which the LLM decides which workflow to follow. And apart from that, we are also adding cycles to this router. That's the reason why it's better categorized or better labeled as a state machine. Perfect. So, let's start with the chains then. Remember this diagram. A chain is this sequence of different nodes that are going to be executed. And the chain that we are going to build combines four concepts. So using chat messages as our graph state, using chat models in graph nodes, binding tools to our chat model, and finally executing tool calls in graph nodes. All right. So let's start with the basic about messages. All right. Because you will see that many of these AI message, human message are popping all over the place with LangChain, also LangGraph. And I just wanted to give you a quick intro to what this is. So chat models, by the way, chat models are the abstractions that LangChain, LangGraph implements for you to avoid having to implement the OpenAI API request or the Anthropic API request anytime you need to interact with one of these models. Everything is abstracted away. So you just need to take the chat model and run .invoke to generate a response. So chat models can handle different types of messages representing various models in a conversation. Here you can see the most common ones have the human message from the user, a message from the chat model, system message where we define the system prompt. This is like a guide to the model's behavior. Tool message, responses from tool calls. This is something that we will see later. And let's build a list of messages. So each message can include like content, the name, and the response metadata. Perfect. So in here, this is a very simple start, a very simple example in which I'm defining a list of different examples. So we start with this AI message, then we append this human message, this AI message, human message, etc. This is really similar to normal conversation, to a realistic conversation between a human, in this case myself, and a chatbot. And if you run this, you will see the final response of the agent. Okay, I think in this specific example, I was asking for so like I'm your virtual travel assistant for Bengaluru, and I was asking for some tips or some good places, good spots to visit while I was in Bengaluru. Okay, so chat models, that's something that I explained you before. And chat models are just basically the way in which LangChain abstracts away all the boilerplate code that you need to interact with the different LLM providers' APIs. Before we proceed, by the way, you will need to check if your OpenAI API key is configured. So I've added this in each one of the notebooks because I think it's easy to configure. You just need to run this, and here you just need to copy and paste your OpenAI key. All right. Okay, so I've just added mine, and now if we run this interaction, this invocation of GPT-4o, it should be working. So yeah, let's wait for the result. Might take some time, which to be honest, I don't know why. And yeah, that's it. So we can see that the result is going to be an AI message because it's the response by the model with a specific response metadata. By the way, and this is just for curiosity, but you can see here there is an AI message. This response metadata, it's interesting because you can see that many of the LLM observability platforms are able to calculate, for example, the number of tokens and the cost per token, etc. So all of this information is encoded inside this response metadata. And for proxies like LightLLM or libraries like that, OpenRouter, LightLLM, the tricky part is that you will need to translate the specific kind of information that each provider is giving you. So yeah, that's like a really tricky part for this kind of proxy libraries that are able to allow you from one single call to access the different providers. But yeah, that's just for curiosity. Okay, so let's keep going. Now that we have the result, you can also run a pretty print, which is also very, very typical. Finally, access the content with this .content. All right. So now that we understand messages and chat models, it's time to understand probably the secret sauce of any agent system that is worth it, or the secret sauce of any LLM system that works well, which is the tool, which are the tools. Tools are valuable when you need a model to interact with external systems. These systems, such as APIs, typically expect structured inputs rather than natural language. All right. And these tools are in charge exactly that. They receive like this, they're a way for the LLM to access these external systems that demand some structured inputs. And that's the task of the LLM, to translate the natural language of the human into these structured inputs for the tool. All right. And you can bind any Python function using LangGraph using this chat model.bind tools to the function. All right. Here you can see an example from LangChain. All right. Like natural language is what is 2 times 3. And the LLM has one tool binded, this multiply, that is going to multiply A and V. The structure tool, whenever receives this command by the human, by the developer, it's just going to generate a set of arguments. And then you manually will be in charge of taking these arguments and calling this tool with the arguments. All right. Perfect. So we're just going to define a very simple tool, the multiply tool, which is contains this A and V, which are the parameters, both integers, and it's just going to multiply A and B. The arguments, of course, are A and B, and this is exactly what we are going to bind as tool. One important detail here is that many people create really poor doctrines, like myself. To be honest, if you want to build some custom tool, if you want to build some complex tool, or if you have an agent that has available a lot of tools, you need to put a lot of effort into creating valuable and highly detailed doctrines, because otherwise your agent is going to perform really, really bad. I mean, at the end of the day, agents are not magic, so you need a way for the agent to know what each tool, what each function is going to do. And that's the reason why you need to put a lot of effort into defining these doctrines in a good way, right? So yeah, let's take our chat model and bind these multiply tools, which generates a new chat model, which is LLM with tools. And now we can simply call this LLM, first of all, with a non-related tool question. Hey, how are you? And now, if I run, you can see that the result is a general answer, a general AI message. All right. The content is just, hello, I'm here and ready to assist you. How can I help you today? But what happens if I ask for what is 2 multiplied by 3? In that case, a tool call is going to be returned. This is very different from the previous message, which is just a string, which is the regular content that you will expect. In this case, there is no content inside the response. And the reason is that this response contains tool calls. Remember that if we go to the diagram, when the LLM establishes that a tool needs to be called, the result is not going to be a response in a natural language. It's just going to be the arguments that you need to use to generate a response. So this tool call is just telling us, hey, you need to use the multiply function with these arguments. This is the ID of this tool call, and the type, of course, is a tool call. Okay, so there is a big difference. And I remember when I was running live this workshop that many people were surprised because they were expecting this tool call to generate the response, but that's really different. I mean, the workflow is the following. You ask a tool-related question, and then the LLM is going to generate a tool call, a message containing a tool call. Then you will need to manually take this tool call result, this tool call that tells you, okay, this is the name of the function and this is the arguments. It's just going to invoke this function with the arguments. And then the result is going to be attached as the context to the LLM to generate a response. This multiply with 2 and 3 is going to generate, when you run the Python function of multiply, is going to generate a result of 6. And then this 6 is going to be attached, is going to be added to the LLM context. And thus, it's going to be able to generate a response to you saying, hey, the multiplication is 6. And by the way, being a human is a bit humiliating that you don't know how to multiply 3 and 2. But yeah, I mean, just a very simplistic example. All right, so now that we understand tools and the difference between tool calls and tool results, which remember are very different, we are just going to continue with our chain example by defining the state. And in this case, it's going to be a bit different than before. Before, we're just using this graph state, completely naive approach. I don't know what it was. Remember that the first state was really like naive, this graph state, which is a string. Right now, here, we are going to improve this state a little bit to make it a bit complex. And the way to do it is to add this messages property. This messages property is defined from scratch in this cell. All right, we are using the type dict, and from LangChain core messages, we are defining this any message because, of course, messages could be of any message. This list can contain system message, tool messages, user messages, AI messages. You follow me. But then there's something really interesting in the next cell because this would be the first, your first idea. If I tell you, okay, I want to create a state that contains messages as the property, right? Because I just want to keep track of the conversation between an AI and a human. But the thing is that LangGraph already implemented this because many people were doing this over and over again. So they said, okay, guys, we just implemented from LangGraph, you can import it. I mean, it's already built and it's this messages state. So if you want to create a state that contains this messages list that has some cool add-ons, like for example, when you add a new message to the state is actually and automatically appended to this list of messages. You will see it in the example below. But yeah, in short, LangChain guys are smart, and they decided that it was better to create a messages state that anyone can simply import, like I'm doing in here. Okay, I'm creating my own messages state, which is just this messages state. I mean, this is completely transparent. It's a stupid way of creating the class, to be honest. You could be using this as it is, but yeah, just to make the comparison with the first one, I decided to go with this naive way. Okay, so now building the graph. We are importing, as before, this LangGraph.graph, importing this state graph, and then the start and the end, these meta nodes that I was telling you about. The node that we are going to generate is this tool calling LM. As input, we have this messages state. Remember, the state that contains these messages as a list of any kind of message, AI message, human message, etc. And what it's going to do is just going to update the property, update the content of this messages property of the state by running this .invoke method to the LLM with tools, with our LLM with binding tools. We're just passing the list of messages, and it's just going to generate a new message. And you might be asking, okay, but in here, you're not appending any message to a list. How is it possible that you are filling up this list with the different types of messages? And that's an amazing question. The thing is that implicitly, that's something that you won't see because LangGraph has already implemented this for us. LangGraph is going to take the result of this invocation and is going to append it to the messages state, right? To the messages property, sorry. So what you will see if you keep interacting, if you keep accessing the messages list, you won't see a list that is being replaced, that is being updated over and over. You will see a list that is growing in size because the results are just appended to the end of the list. All right? Perfect. So first of all, as I was saying, we defined this node. We defined the builder object using the state graph with the messages state. We add this single node, this tool calling LLM, and now two edges. Two edges. The first of all that connects the start node with the tool calling LLM, and the second one that connects this tool calling LLM node and the end. We compile and we display the diagram. I mean, I think you won't find something as simple as this. But yeah, we have three nodes, the start, tool calling LLM, and the end. And this is our first simplistic chain. Now you can, of course, invoke our graph with the messages. As input, we are just passing this, "Hey there, I'm Miguel," as the input message. And we are just looping through the different messages in the state. Because, by the way, whenever we invoke these messages, it's just the state. It's not properly the messages list, it's the state. And that's the reason why I need to access the messages property from the state. So this is, I know it's a bit misleading now that I check it, but Graph Invoke is just going to provide us with the state, like the last state, the final snapshot of our workflow state that contains, of course, the final snapshot of the messages property. All right. And that's the reason why if I loop through the different messages, I can just see this conversation. But now what happens if I ask for a multiplication? Because remember that we are using inside the node this LLM with tools. All right. What happens if I ask for a multiplication? So what's going to happen is that we are going to receive, as expected, a tool call that tells you, okay, you need to use the multiply function, the multiply tool. This is the call ID. The args that you need to use to solve your query are just A equals to 10 and V equals to 3. Because remember that the query was multiply 10 and 3. All right, so yeah, let's run this again. You can see that the output is stable. All right, so now we understand how LangGraph works, we understand how chains work, and now it's time to go with the router, which is something much more interesting. So you can think of the router as designed as a pattern in which the chat model is going to decide, based on the user input, whether to respond directly or to call a tool. All right. Of course, we could use a router to connect any tools that you want, but in this case, we are just going to use it for the LLM to decide, should I call a tool or should I skip the tool? Because remember that in this case, we are just calling all the time with the LLM with binder tools. Right now, we want to skip this and we want for the LLM to decide if a tool is even necessary. All right. So to extend the chain example, we are going to do two things. First of all, add a node that will call our tool, and add a conditional edge that will look at the chat model output and route to our tool calling node, or simply end if no tool call is performed. So again, we are just defining this multiply tool, and we are just, you could even just copy or use like the previous defined tools, but just wanted to start from scratch again. So we are importing the chat OpenAI chat model. We are just defining here the tool that we are going to use. And here you have a definition of the LLM and the LLM with binder tools. All right. And now we are adding something a bit different than before. We are adding a tool node. And this tool node is something really interesting that the LangGraph team introduced to LangGraph. Because the thing is that, do you remember when I was explaining the tool workflow? All right. You have the LLM, you ask for a tool related question, and the LLM generates a tool call. And then you need to manually take this tool call, take the tool, run the Python function with the arguments that the LLM has decided, take the result, and introduce or append this result to the context of the LLM to generate an actual response, okay, in human form, in natural language. Okay, so that sounds really boring, to be honest, and really repetitive. And that's the reason why LangChain introduced this tool node, okay? So the code is going to be a bit different than before. Well, you can see the state graph, the start and the end, the messages state, but now you will see two additional lines. This LangGraph pre-built tool node and this LangGraph pre-built tools condition. All right. The tool calling LLM is going to be just the same as before. We're just defining this state graph, this builder object, and we have one additional node. We are keeping the same as before, this tool calling LLM that is just going to run the actual invocation of the LLM with binder tools. But we are also adding another node, which is this tool node that contains a list of all the available tools. For our specific example, there's just one tool, the multiply tool. Then we are adding the first edge, which is going to connect the start node with the tool calling LLM. But in this case, we are adding a conditional edge that is going to connect the tool calling LLM with this tools condition. Well, not with this tools condition. Remember that with the conditional edges, you needed to provide a function for the edge to decide which node to select. All right. So this condition is just this tools condition. And I've put here a comment that explains what is happening. So if the latest message, the result from the assistant, okay, when we call the LLM using the chat model, is a tool call, then tools condition routes to the tools node, okay, to this one. So the tool is going to be executed. If the latest message, the result from the system, is not a tool call, then tools condition routes directly to the end. This is something that you will see really clearly in the diagram below. All right. Then we simply add the edge that connects the tools node with the end node. We compile and we display what is happening here. And what you can see is a very, I think, easy to understand graph. We have the state node that connects with the tool calling LLM. where the actual invocation to the chat model is going to take place in. If there is a tool call, we're going to go through this right path, all right? And the tools node is going to be invoked. In this specific example, there's just one tool available, the multiply. So it's not a big deal. The tool, the workflow will go this way. The tools node is going to be triggered, and the result is going to be sent to the end node. If the tool call LLM does not generate any tool call, then it's going to go directly to the end node, and that's the end of the workflow run. Okay, now let's see what happens if I ask for what is 2 multiplied by 2. Okay, so first of all, we have the message, the human message that I've just sent. Then we have this tool call, this AM message that tells me, okay, we need to use a multiply tool. This is the call ID, and this is the args that you need to use to your multiply tool. A equals to 2 and V equals to 2. But finally, and this is something we didn't see in the previous examples, there is a tool message that contains the name of the tool that is being triggered and also the value, okay, the value of the result. And this is exactly what the LLM is going to use to generate a response. In this case, 4, which is accurate, right? Perfect. So now we understand another cool pattern. As I mentioned by the beginning of the video, one of the patterns that I use the most in many of my projects, the router pattern or the router design or whatever you want to call it. It's just basically using a chat model to route how the workflow is going to proceed. Do you need to go to step 1? Do you need to go to step 2 or to step 3? Do you need to use a tool, or do you just ignore the tools and go directly to the end of the workflow, generate a natural language response to the human with no tool related content? So that's basically the reason behind this router design. Now we are getting into the most complex architecture, let's put it that way, that we will build today, the React agent, the React loop. Because in this place, in this kind of architectures, we are going to introduce loops. So we are going to proceed very similarly to the previous evolution from chains to router, just going to take the router and evolve it a little bit. And that's how React agent is born. So you can think of it, as I was saying, as an evolution of the router pattern. In the router above, we invoked the model, and if it decided to call a tool, we return a tool message to the user, right? But what if instead we pass that tool message back to the model so that it can be refined even further? So that way it gets to decide what's next, call another tool or respond directly. Because in the other approach, you are just constrained to using one tool, like just one single tool call. I mean, you could equip your agent with multiple tools, but if the agent needs to multiply, then divide, and then add two numbers, it's impossible with the previous approach. You just need to create one giant function that contains all the logic inside. But what if the agent needs to use one tool first, then another one, and then another one? With a router pattern, it's impossible. That's the reason behind this React pattern application. React, by the way, stands for Reason plus Act and can be easily understood by the following diagram. This is part of my first open source course in the neural maze, where I implemented from scratch the 4 agentic patterns. This is the third pattern, the planning pattern, and one of the huge exponents of this pattern is the React pattern. So yeah, if you want to check it out, you can go to the Neural Maze GitHub organization or to the YouTube channel and just check my video or the code related to the agent design patterns. I think you're going to love it. All right, so to test the React architecture then, let's create 3 tools instead of 1. Multiply tool, add tool, and divide tool. You can see that the complexity here is just the same as before. I mean, we are not creating huge, complex tools in here because, I mean, it's just, I just want you to understand what's happening. In future notebooks, you'll see how tools are going to be a bit different because we want to implement some RAG-related tools and stuff like that. Okay, so now let's bind the three tools, as always, to the OpenAI chat model. We have, first of all, this LLM, and then we have this LLM with tools. This is something that you are already proficient with after the previous, after this hour of content. And now let's create a simple node for defining the assistant behavior. Okay, as we did before, we need an invocation of the chat model. But for this example, I just took the liberty of adding this system message, okay, to guide or to generate some general guidance of how the agent, how the LLM application should behave. The system message is really straightforward. So you are helpful assistant tasked with performing arithmetic operations. All right. And the type of message, the LangChain core message, is of type system message. Perfect. So let's keep going. And now let's build the graph. You will see that it's very similar to the example before, but there is like one subtle difference. So as always, ports are basically the same. We are just using here the state graph to generate the builder object. We are adding this first node, which is the assistant node. Remember that this node is just in charge of running the invocations. And then the tool node that contains all the logic for running the tools or not. We are just adding the conditional edge, but this is the important difference because now the tools node points back to the assistant node, not to the end node. And this creates a loop, all right? The beginning, in the previous example, we were linking together tools and the end node. Right now, we are replacing the end node with the assistant. So we are actually creating a loop. In fact, if you visualize what's happening under the hood, you will see that, yeah, we have the start node connected to the assistant. That's usual. That's same as before. Assistant is also connected to the end in case there is no tool call, but this tools node is not connected to the end in this case. It's just connected to the assistant back again. It's creating an actual loop. So let's try it out. And in this example, let's put things a bit harder for our agent, right? So instead of just saying add 10 and 5, let's say add 10 and 5. Multiply the output by 2, and then divide the output by 5. So let's run this, and let's see what our agent does. Is it able to perform such a complex computation? So yeah, at 5 to 5, this is the human message. The first call is a tool call that is just going to invoke the add with two arguments, A as 10 and V as 5. Generates a tool message of a value of 15, then it multiplies 15 and 2 to generate 30, and finally it just divides 30 with 6 to generate a final value of 6. And the agent is really polite and it provides the final message, which is that the final result is 6. Let me do it with my human mind. So 15 multiplied by 2 is 30 and divided by 5 is 6. So yeah, I have achieved the same result as the agent. So I guess we are both right. And this is essentially how you can build a React agent inside LangGraph. And this is essentially what you will need to perform some complex planning operations, some complex reasoning operations with LangGraph for your agents. And by the way, this is exactly, let me see the diagram. This is exactly the architecture, the structure that we are going to use for the rest of the workshop when we try to implement our Telegram bot agent. All right, so let's get back to Canva, to my presentations. And let's do a recap because I know it's been quite intense. I've been talking for 1 hour about LangGraph. I know it might be arid. I know some of you might be really proficient in LangGraph and you might just want to get into the funny part, to get into how to take all of this knowledge and put it into practice to generate the bot, the bot agent, the Telegram bot agent. But I think it's necessary. And I hope this is helpful for some of you who might be starting to journey or might know nothing about LangGraph. So yeah, to recap, we have explored how LangGraph can be used to build agentic workflows, ranging from simple systems to more complex architectures. We covered how to use the three fundamental components of the framework, so nodes, edges, and state. We also implemented a router, which will serve as the core architecture for this workshop. Remember that it's a router, but also with some loops, so you can understand it as some kind of state machine. And now it's time to explore a very important component of any agent architecture, the memory. So in the next section, we are going to delve deep into memory, both short-term and long-term. So yeah, I'll see you there. What's up, folks? So let's get into the memory of our system. So as I mentioned at the beginning of the video, in agentic systems, there are two types of memory, short-term memory and long-term memory. Short-term memory is also known as the working memory and refers to all the context available to LLM at the time of generating a response. All right, and long-term memory refers to all the information stored in external databases that the LLM can access when it needs to, based on the relevancy in the conversation. Right, so we are going to start with the short-term memory, as it's probably is the simplest to implement, and then we are going to move into the long-term memory, where we will work with vector databases, in particular with ChromaDB. For short-term memory, I just chose SQLite because it's really easy to use, really easy to install, and it's really easy to integrate with LangGraph systems, and that's the reasoning behind this choice. So the short-term memory in LangGraph will involve three steps. First of all, we will store the message history inside the graph state, remember, in the message property that we already used in the LangGraph crash course. Then we will summarize the conversation to reduce the token consumption. And finally, we will use external database to store the graph state, because this short-term memory could be also stored inside the memory. The problem, by memory I mean the computer memory. The problem is that whenever we restart the session, whenever we close the session, all of this memory will be erased. And that's a problem if you want to keep track of the conversation, if you want some stateful agent to keep track of the conversation with the user, right? Perfect. So you will see that from now on, everything will be much lighter in terms of theory and more intensive in terms of code, which I think is much funnier, right? So for this first system of the agent memory systems, just head to the 2.1 short-term memory collab, and you should see something like this, right? So in this coding session, we will implement a short-term memory from a very basic solution to more advanced approaches, right? We will start, let me connect the instance first of all, and we will start with in memory, and then we will move into some external databases where we can allocate, where we can store or persist all the different, basically the LangGraph state, right? First of all, we will store this LangGraph state in the memory, and then we will move to external databases. All right, so it seems it's working now. Remember that you will need to copy your OpenAI API key and paste it in here so that it's accessible from the environment variable. Let me do it. All right, so I have my API key already defined in the environment variable. And now I'm just heading to the first implementation of our short-term memory, right? So first of all, we are importing the chat model for OpenAI models, then the messages state that we already know, and finally some messages, specifically the human message and the system message. We are using GPT-4o mini for this one. And as always, just define the state with this, just define the first node, the assistant node, that is in charge of invoking the chat model with the messages, defining the state. And that's basically it. I think this is pretty straightforward for you since you are already LangGraph ninjas after the crash course. All right, so now it's time to build the graph. We are just defining the workflow, this object that we will use to add the nodes, to add the edges, and to compile eventually the graph. As the node, we're just defining the assistant node with this function that we've just defined. We are adding an edge that connects start with assistant and assistant with end, and finally just compiling everything. And you can see that it's a very straightforward and simple workflow. I mean, it has 3 nodes. Two of them are these meta nodes, the start node and the end node. And now let's invoke it. So the thing is that if I try to invoke this, providing some information about myself, hello, I'm Miguel, you will see that the assistant is being really polite with me, telling me, hello, Miguel, how can I assist you today? But what happens if I ask my name again? So the problem here is that if I ask my name again, remember my name, the assistant will tell me something very unpolite or, very weird if we are expecting some human-like conversation. It's telling me I don't have the ability to remember personal information or previous interactions, but I'm here to help. How can I assist you today? Okay, so what is happening? Basically, this is because state is transient to a single graph execution. So whenever we execute a graph, whenever we invoke a graph, that state is transient. It's going to disappear after we invoke the graph. Of course, this limits our ability to have multi-turn conversations with interruptions, like building a simple chatbot. But we can use persistent to address this. Of course, there are multiple ways of adding this persistence. We could be persistent inside the computer memory, like the RAM, or we could be doing that with external databases. For this first use case, I'm just going to use this memory saver, where we are going to use the in-memory key value store for graph state that LangGraph already implements. So to import this, we just need to use LangGraph checkpoint memory and import the memory saver class. We are creating an instance of this memory saver class, and we are compiling the graph. But remember that in the previous notebook, in the LangGraph crash course, we were using the compile without any additional parameter, like this. Right now, we are adding this parameter. Let me put things a bit bigger. We are adding this right here, okay? Set pointer equals to memory, and memory is this memory saver. When we use the memory, we need to specify a thread ID. And this thread ID will store a collection of graph states. Why is this thread ID necessary? Because suppose we are having an assistant, like for example, the one that we are going to build today, a Telegram bot. This Telegram bot ideally will have conversations with potentially millions of users. If you manage to do something really cool and you put it out live and eventually it's a complete success, then maybe you'll have thousands of people, millions of people talking to your Telegram bot. What's the problem with that, apart from the token usage, of course? The problem is that you need to select or you need to isolate the conversation of the assistant with each one of the users. And that's the reason why we are adding this thread ID. The thread ID is going to isolate and it's going to group the same events inside the same partition of data. Let's put it that way. All right. So whenever we interact with or we invoke the graph, a graph that has a memory checkpointer attached to it, we need to provide a thread ID. Okay, because everything will be stored, will be saved in a thread. Right? Okay, so now that we have this memory saver and we have compiled a graph with memory, with a memory checkpointer, we can just specify a thread like this. So config equals configurable and thread ID. I mean, I'm just using this one because I'm just having a one-to-one conversation with this assistant. Ideally, you will use something like UUIDs or any other identification that you see fit. Now I'm creating the messages, a very simple human message. Hello, my name is Miguel. And I'm just invoking the graph with the memory attached with the list of messages. All right. And important that the difference from before is that now we need to pass the config. Okay. So now, oops, I think I didn't run this. Yeah, like this. And now let's run this cell. All right. So this is very similar to before. Hello, my name is Miguel. Hello, Miguel. How can I assist you today? Let's see if the assistant remembers us now. So, hello, until today. Hey, can you say my name? Do you remember it? Yes, I remember your name. It's Miguel. How can I help you today? So right now, it's working. Adding the checkpointer fixes the issue. Our graph has memory now. But now, the problem with this approach is that if we keep adding messages or interactions, conversation turns to this messages list, there will be a time when the amount of tokens is going to, drive you to bankruptcy, basically. And if it doesn't, if you're rich, what is going to happen is that the memory context of your LLM is going to explode. So you will eventually start getting errors saying that, okay, this is out of the memory context. Okay, so in this case, what you need to do is to add a summarization step. You need a step in your workflow, in your graph, that will take care of summarizing the conversation so far. Okay, this multi-turn conversation between the human and the assistant. Right, let me show you how to do it. So again, we are just defining state, but in this case, we are adding an additional property apart from the messages property. And this property is called the summary, which is a string. So now we'll set up a node to call LLM, adding a summary to a prompt if one's available. So this is basically the same as the assistant node that I defined at the beginning of this notebook, in which the only expected output from this node, or the only expected behavior, is to run an invocation with an LLM to generate a response. The only difference is that in this case, in this specific node, we are also considering to add to the context of the LLM the summary, if one summary exists. So call model. So first of all, we are just getting the summary if it exists. And then if there is a summary, then we add it to the system prompt. All right. So if summary, we are just taking the system message, which is the summary of the conversation earlier. And we are passing as F string, the summary that we just get from the state. Of course, if it's available, it might be that there's no state so far, and it's just an empty string. And finally, append summary to any newer messages. All right, so for the messages, we're just taking the system prompt and adding to it the list of messages so far in the conversation. If there is no summary, then messages is going to default to the list of messages in the conversation, the chat history, basically. And finally, just run an invocation with the list of messages, generate a response, and this is what we are going to return to update the state, to update the messages property from the state. Okay, so let's run this. And now let's go to the actual summarization, because this is just taking into consideration if a summary exists, then take this summary into consideration when you generate a response by the LLM. But how are we actually generating this summary? So in this second node, we'll create a summarization step. And just a heads up, we will use this class from LangGraph, this remove message class, to clean up the state once the summary is created. This is a very fancy class, a very hands-off helper class that LangChain has enabled for us to use whenever we want to delete some messages from the chat history. Okay, so summarize conversation as any other node is just taking as input the state. We are taking the summary if it exists, and now create our summarization prompt. All right. If there is already a summary present on our state, we are just taking this this prompt. So this is summary of the conversation to date, and this is the already existing summary. Extend the summary by taking into account the new messages above. Okay. So create something that takes into consideration all the summary of the conversation so far, and then extends this summary with the new information. If there's no summary, then it's even an easier prompt, create a summary of the conversation above. Now we add the prompt to our history. So we take the state messages, the property from the state, and we add this human message, which is the prompts that you can see in here. And finally, just generate a response using LLM.invoke. Apart from that, this is something that I've put here by default, but you could even extract this away or create a parameter to tune the number of messages that you're going to delete. This is up to you. I just hard-coded it because, I mean, it's just for the sake of the example, for the sake of learning, of building something really, really simple. So I didn't find it necessary to add more complexity. But if you want, of course, you can take this number and just take it out as a parameter to a node or to the function. Well, in particular, you will need to put this as some kind of parameter for the state for the graph. But yeah, it's up to you. So with this line, what we are doing is removing or deleting all the messages in the chat history, but the two most recent messages. And finally, we are returning the updated state. In the previous node, we were just updating one property of the state, the messages. In this new node, we are updating two properties because we are updating the summary and we are updating the messages. And the way in which we are updating the messages is by sending this list of remove messages. And LangGraph will take care of interpreting this as a way to delete the signed messages from the chat history. Perfect. So let's run this. And finally, there's just one missing piece because we also need to add a conditional edge that checks the conversation length to decide whether a summary should be generated. Basically, we need to create something that tells the workflow when the summarization step should be triggered. And we've called this the should continue conditional edge, also receives the state, and it's connected to either the end node or to the summarize conversation node. As input, just taking the list of messages, and if the length of the list of messages of the chat history is above 20 messages, then it's going to summarize by connecting the previous node to the summarize conversation node. If it's below 20 messages, then it's just going to end the workflow. All right, so let's run this cell. And finally, let's build the graph. So first of all, we are just importing the memory saver. This is something that from now on we will do non-stop because it's important to add some memory to your agents. We're just defining the workflow as always, adding a node, the conversation node. Remember the call model that is going to take into consideration the summarization step if present, and then the other node, which is the summarize conversation node. Then we are defining the three edges. Two are regular edges, this edge that connects start with conversation, and this other edge that connects the summarize conversation with the end. But there's a conditional edge we've called that connects the conversation node with either the end or the summarize conversation node. Okay, and remember that this conditional edge is defined, the logic of the conditional edge is defined in this should continue Python function. All right, here we're creating an instance of the memory saver, of the memory checkpoint, and we are compiling our graph with this memory object as the checkpointer. And as always, we are just printing how it looks like. And it looks pretty cool, if you ask me. So we have the start node, the conversation node. If there's no need for any summarization step, then it's going to connect the conversation node to the end node. If there's a need for a summarization, then the conversation node is going to be connected to the summarize conversation node. And only then, once the conversation has been summarized, we can finalize, we can end the workflow run. Alrighty. So this is the way in which you will summarize conversation. And to be honest, this is something you shouldn't skip when you are building like real world applications, because otherwise your system might explode in very short time. To finalize, to end this short-term memory demo or tutorial, I just want to show you how to add external persistence, because in this example we are using this memory saver, but this is a in-memory key value store, which means that if I like runtime, if I restart the session and I disconnect from this machine and connect to any other machine, my memory is going to disappear because the state is going to be deleted, right? That's the reason why we want to add external persistence. Okay, so that's the point in which adding a more advanced checkpointer comes in, one that can work with external databases. Which database have I chosen? SQLite. This is the database that we are going to use as our checkpointer to store externally the LangGraph state. So we are going to first of all import SQLite 3. This is the DB path and this is the connection. In fact, if you go here, yeah, you can see this sample.db, which is the database that we've just created with SQLite. All right, and now instead of importing from LangGraph checkpoint memory, we are importing from LangGraph checkpoint SQLite. And instead of memory saver, now it's called the SQLite saver, but it's fairly the same. We can compile the graph we defined previously, but with a different checkpointer now. Instead of the memory saver, this checkpointer is a SQLite saver, but the appearance is exactly the same. I mean, we've just modified the way in which this graph, or to be more specific, to be more precise, the state of this graph is going to be stored. Instead of an in-memory store, it's going to be stored externally in SQLite. Now let's interact with our graph. So the result is going to be really similar. So hello, my name is Miguel. But now to show you that this works, we will restart the notebook kernel, and you will see how even if we restart, since this example DB, this SQLite database is still present, the agent will still remember us, right? So runtime and restart session, okay? So we are going to restart, and you will see that this example DB is still present and everything is green. So let's start again. Let's install all the things that we need, because of course the Python definitions, the library imports, etc. are gone. But the important stuff, the state of the graph that we have been using, is still in there, and that's the important thing. So yeah, again, we need to put the OpenAI API key. All right. We just defined every node, edge, the workflow definition again, because of course this is all gone. And now let's ask the agent, hey, can you say my name? Do you remember it? And if everything works correctly, when we defined here this checkpointer in memory, it means that whenever we start a new invocation of the LangGraph workflow, this workflow, LangGraph, is going to retrieve the state, the latest state, from the example DB, from the SQLite database. All right, and since I told the agent that my name is Miguel, you can see here that, hey, can you say my name? Do you remember it? Yes, your name is Miguel. How can I help you today? So all of this conversation was successfully stored inside the SQLite database, and it's been retrieved successfully as well, which is very good news. So for our Telegram bot agent, we are going to follow a very similar approach to the one I've been teaching you here. We will use SQLite as a short-term memory. Put in different words, we are not going to use a memory saver. We are going to use an external database to save the state of the graph. All right. Okay, so this is everything for the short-term memory. In the next section, we are just covering the long-term memory. So I'll see you there. All right. So let's get into the long-term memory. So the long-term memory in LangGraph will be implemented using ChromaDB. First of all, we will download some documents and store them in the vector database, ChromaDB, and then we will retrieve these documents from the vector database when they are relevant to the user question. So it's just a RAG application, agentic RAG application to be more precise, but yeah, that's basically it. In here, since I'm not sure the amount of knowledge that you have about RAG, agentic RAG, etc., I just wanted to give you an introduction. If you know RAG, if you know about agentic RAG, if you've read some of my articles about it, you can skip this short introduction. If these are new words for you, then I recommend you to pay special attention. So the diagram that you can see on the left is a traditional RAG pipeline or a RAG application. RAG stands for Retrieval Augmented Generation. And let me summarize what's happening here in the diagram. So first of all, we have a set of documents, and we are going to split these documents into multiple chunks, into tiny pieces. These pieces are going to be sent through an embedding model that will transform each one of the chunks, each one of the pieces, into embeddings, into vector representations of this text. That is going to be stored inside a vector database. Remember that for our use case, we are using ChromaDB as this vector database. Here in blue, you can see a rectangle containing query. And what is a query? You can understand query as the user message. Suppose that these documents are financial information for a company. And a user is asking for the balance sheet or for the income statement, how much income the company has achieved the last quarter, for example. So this question, this query, is going to be passed through the embedding model again and sent to the vector database. And what is going to happen here is that the vector inside the vector database, we will see for the embeddings that look more similar to the user query. Okay, we will run some similarity search and get the chunks that are more relevant, that are more similar to the user question, to the user query. This is the context that I'm highlighting here. All of these relevant chunks, all of this information relevant to a user question. And that's the reason why I call this augmented, because this context is going to be added to the prompt template or to the prompt, to the input prompt, or you could even say it in terms of context engineering, that this context is going to be added to the LLM context, to all the information that the LLM is going to consider before providing a response to your question. All right, and that's exactly what you can see in here. Okay, the LLM is going to take this augmented context, this augmented prompt, and it's going to return a response. Now, what's the problem with this approach? The problem is that no matter the query that the user is sending, no matter the message that the user is sending, we will always have to send it through the embedding model. So we will always have to run this similarity search inside the vector database, and we will always have to include all of these additional tokens inside the augmented prompt and generate a response. But it might be the case that these chunks are not relevant for the question, because suppose I say something like, hey, my name is Miguel, nice to meet you. Is this flow necessary? I don't think so. And that's how agentic RAG was born. That's the reasoning behind agentic RAG. In agentic RAG, we are replacing this deterministic flow with a retrieval agent that is going to decide if the search step or the retrieval step is necessary, or if it's enough to generate a single response with the LLM. All right, so suppose I'm here, I'm using the example message that I was telling you about. So, hey, my name is Miguel, how are you? In this case, the retrieval agent is going to take into consideration my message and it's going to evaluate it as not relevant to all the information that we have stored inside the vector database. So it's just going to generate a regular response like, hello, I'm an assistant, I have no name, or hello, I'm really fine, how are you, what can I assist you today? Typical assistant responses. But what happens if I ask about the financial statements for my company last quarter? In that case, the retrieval agent is going to say, this is important. I mean, there's some information inside the vector database that I can use to provide a better question, a more grounded answer, to Miguel in this about this question. And that's the reason why the retrieval agent is going to fetch all the relevant chunks from the vector database and is going to add all of these chunks to the context before providing an answer. All right. So that's exactly what we are going to build in this tutorial, in this coding session. So go to Colab again and open the Tutu long-term memory Google Colab. All right, so I have it in here. As always, let's connect to the instance. And just set the OpenAI API key and install some relevant dependencies. So let me take the OpenAI API key. Okay, perfect. So now that the OpenAI API key is set, let's go into the interesting part. We will start with the indexing bit. In any RAG application, there are two phases. First of all, you need the indexing phase, and then you need the retrieval phase. All right, so the indexing is thing that I told you about when we were taking all the different, let me go to the slides again. So indexing is this side over here. When we are taking all the documents, we are creating the chunks, and we are just using the embedding model to create the embeddings out of the chunks and storing all the embeddings inside the vector database. Right, so here you can see that we are loading all of different documents. We are splitting these documents into chunks. We are generating embeddings for each one of the chunks and storing everything inside a vector database. So the first thing to do is to download some interesting documents that we are going to chunk and then to embed. Perfect. So relevant imports in here. First of all, from LangChain OpenAI, we are importing OpenAI embeddings. This is the embedding model that we will use to generate the embeddings from the chunks. Chat OpenAI, you already know this one, the chat model. And from LangChain Chroma, we are importing this Chroma class. This makes possible a collaboration or the interaction between LangChain and ChromaDB. Perfect. So the embedding model, the one I'm going to use is this text embedding 3 large. And as for the chat model, for the OpenAI model, GPT-4o mini. The Chroma instance, the Chroma database, is going to be called, the collection name is going to be called a sample collection. Inside the Chroma vector databases, you have collections which are somewhat similar to a table. So we are defining this example collection, the embedding function that you can attach to the Chroma instance so that whenever you try to store a chunk, it's going to be automatically embedded. The embeddings is the embedding model, the OpenAI embedding model, and the persist directory, is the long-term memory DB. Okay, so a few minutes when we start putting some vectors inside the vector database, you should see here the vector database, okay, like a file containing the Chroma instance. Perfect. So now we are going to follow a very traditional tutorial, like a hello world for RAG applications. This little log is one of my favorite blogs whenever I want to really get into the depth of agents, of deep reinforcement learning, of diffusion models, whatever complex topic in the AI field. Highly recommend you this little log. And I saw a LangGraph tutorial that I have adapted for a use case in which they were like embedding some of the articles that in this blog. So I thought, why not? And I mean, LLM-powered autonomous agents. I think this is the best article that an agent should embed. I mean, there's some kind of meta reality involved here. It's really, really interesting. So yeah, first of all, we are just going to download the document, this article, this LLM powered autonomous agents from, let's block this, from the URL, using some code from Beautiful Soup. That's just to do some scrapping and to format the HTML page, etc. We are just going, as I was saying, to download the document. And here we are just generating, like creating the text splitter, the recursive character text splitter. This is necessary to create the chunks out of the documents. In here, we are effectively generating all the different splits, all the different chunks. And then if we keep scrolling down, you will see that there's another cell in which we are going to effectively start adding all the chunks, all the documents inside the vector database. Okay, so let's run this first, which we just downloaded the document and created the text splitter. And in here, you can see in all the splits that the splits have been generated, the chunks, okay? Here you can see the first chunk that contains the following text, so LLM Power Autonomous Agents, date June 23rd, 2023. And if you go here, you can see that it's the first bit of the article. Okay, so it seems to be working really fine. And now, the final step, which is to index the chunks. So we just need to access the vector store object that we define at the beginning. Here, this chroma object, and just add all the documents. So to the documents parameters, we are passing the list of all the splits of all the chunks that we have generated from this article. All right. Perfect. So after we run this cell, the indexing part will be ready. This means this green click, this green ticking here means that all the chunks have been transformed into embeddings, into vector embeddings, and all of these embeddings are now safely stored, persisted inside the collection that we have created in Chroma. In fact, you can see that right now there is a long-term memory DB instance here persisted in disk that contains all that we want, that contains all the vectors, all the embeddings for the chunks. All right, so let's quit this. Perfect, so now we go to the other step of any RAG application, of any RAG system, which is the retrieval step. This is like the real-time step. You can take this, the indexing part, as the offline step, in which we are taking all the bulk of documents and we put in all the documents inside the vector database. And you can take the retrieval step as the online phase, in which, depending on the user message, we are going to fetch one chunks or other chunks. Okay, so now that all the chunks, as I was saying, are indexed, we need a way to access the information stored in Chroma. Of course, we could query directly. So, of course, we can take the vector store object and run the similarity search ourselves, like manually. Here, I'm just asking for what is task decomposition. And k equal to 1 means that I'm just going to take one of the neighbors. Okay, we could put here 3 neighbors, 10 neighbors, whatever you want. So we are running the similarity search, and as the results, we are getting just this document. If you take a look at what is discussing, you should probably see in here task decomposition, and it's talking about domain PDDL. So this is automatic planning, which is a subfield of AI, in which the plans, like automatic plans, are split into different tasks that the agent or the automata, the agent, needs to execute in order. So I think, I mean, the document is probably the most relevant out of the article. And of course, here you have like explicit mentions to task decomposition can be done by LLM, blah, blah, blah. So yeah, I think it's a good match for the article, which means that it's working reasonably well. But there's also a way to retrieve all of this information, and this is the way in which we need to equip our agent, because you don't want to run this manually every time. You want to create some kind of tool so that the agent is able to access this tool whenever it sees fits, right? Remember agentic RAG. The retrieval agent is going to decide, okay, should I go to the vector database and fetch some relevant chunks, or should I just generate a regular answer with my LLM, right? So first of all, we are just defining this retriever, okay? Vector store as retriever, and then we are creating a tool out of this retriever, okay? Create retriever tool. We are passing that retriever, the name of the tool, and the description. And this is very important because the agent is going to use both the name and the description to really understand when to use this tool. Okay, so let's run this. And some fun fact, do you remember at the beginning in the LangGraph crash course when I was talking to you about the runnable interface, the runnable protocol? You can see here another example. The retriever implements as well the runnable interface. And that's the reason why we can invoke it as well, the same as we do with the graph, with chat models, with tools, etc. Everything in LangChain, almost everything, implements the same runnable protocol. That's the reason why you can use this invocation. Okay, so retriever invoke, this is going to generate, again, the same document. That's the composition can be done, blah, blah, blah. And the same can be done with the retrieval tool. And this is the important stuff, because the retrieval tool is going to generate the same output as the retriever, but it has the syntax, it has the specific nature that turns it ideal for the agent to use it. Perfect. So now we need to add this retriever as a tool, remember, to our graph, and that's very easy if we use again the tool node. Remember, this is the way in which LangGraph lets us introduce tools as nodes inside our workflows, which is really cool because we don't need to do anything manually. LangGraph takes care of doing everything automatically by using this tool node. Okay, so let's create a graph. So first of all, just create the state graph, import the state graph, start, and the messages state, this tool node and this tools condition. We are binding some tools to the LLM, to the chat model, in particular the retrieval tool, and we are creating our typical node, the assistant node, which is in charge just of creating, of invoking the OpenAI model, the GPT-4o mini. You can see how easy it is. I mean, LLM with tool, invoke, and the state that contains the chat history, right? This state messages that contains all the list of the messages between the exchange between the human and the AI. Perfect. Now we define the workflow. Remember that this is the object that we will use for adding the nodes, edges, compiling, etc. We are adding the first node, which is the assistant node, using this function that we defined a few lines above. We are also adding another node, this tools node, that is defined by tool node, by this pre-built class that LangChain has implemented for us. The available tools are just one, the retrieval tool. And now let's go with the edges. So the first edge is going to link the start node and the assistant node. And the next edge is a conditional edge that is going to link the assistant with either the tool node or the end. Remember this because we saw this when we were talking about the last two examples in the LangGraph crash course, about the router and also about the React pattern. You can use this conditional edge, this tools condition edge that is going to connect to the tool node or to the end, depending on if the agent finds a tool call inside the response. All right. So this conditional edge is just going to check for the response of this invocation. And if the message that is returned as the output contains a tool call property, the tool call property exists and is not empty for the response, it means that a tool is needed. And if a tool is needed, then the assistant is going to go through this way. It's going to connect to the tools node. If there are no tools available in the response, then it's going to connect to the end directly. All right. But here's a catch, because in the traditional router approach that we did in the LangGraph crash course, in the first hour of this video, we were connecting the tools directly with the end node. But do you remember what we did when we were dealing with the React pattern? Exactly. We connected the tools with the assistant to create this loop so that the agent is able to refine and to evaluate if the response is necessary. It might be the case that we are returning some information, some chunks from the vector database, and the agent with this information decides that, okay, it's not enough. I need to search again in the vector database to get more relevant chunks. That's exactly the reason why you can see a loop in this interaction between the assistant and the tools, because we want to force this loop so that agentic RAG is correctly implemented. We want the agent to decide when to go to the vector database, and we want the agent to be able to refine the search. We want the agent to be able to search one time, a second time, a third time, as many times as it fits necessary to get all the relevant information necessary to generate the optimal result or the optimal response. Okay, so yeah, that's the conditional edge, and we're just adding, as I was saying, the add edge that connects the tools and the assistant to close this loop and to implement a proper React pattern in here, like a React loop. We are just compiling the graph. In this case, I didn't add a short-term memory because, I mean, it was not necessary for this simple demo, but in the next, in the Telegram bot, of course, that's something that we don't want to miss. And finally, just display everything. So display here the diagram, which you can see the start node, the assistant, the connection to the end in case there are no tool calls present, and also this closed loop that connects the assistant with the retrieval tool. Remember that this retrieval tool is in charge of fetching relevant chunks from the vector database, from ChromaDB. And now, if I ask our agent, what is task decomposition? This loop, this workflow is going to be activated. If you see the results, you will see, well, let me print in a better way. You will see a very structured and cool response that is going to take just this information, this relevant chunk, as context for the LLM to generate the optimal result, the optimal response. All right, and here you can see that as a composition involves breaking down, etc., etc. So the LLM has fetched all the conversation so far between the user and the assistant. It has also fetched the relevant chunks for the user question, has taken into account the user question, and then with all of this context, it has provided this response. And that's exactly how long-term memory is going to work for a Telegram agent as well. But yeah, this is everything for this section about long-term memory. In the next section, we will cover speech-to-text systems and also text-to-speech systems with LangGraph. Okay, so yeah, see you in the next session. Bye-bye. Okay, so let's get into the two next systems, the STT system and the TTS system. The STT is the first one that we are going to cover, and the STT, the speech-to-text system, turns incoming voice notes into text, right? We need this system if we want to transform the user voice notes from Telegram into text our LangGraph application can process. What do I mean by this? Whenever we send an audio note using our Telegram, like sending a voice note, whatever, telling anything we want to the Telegram bot, this audio note is going to be transcribed with a STT system. This audio note is going to take the speech contained in the audio note and it's just going to translate, to transcribe, to be more precise, to transcribe this audio into text. And this text is going to serve as input to the LangGraph workflow. All right? I think that workflow is pretty clear. And the model that we will use as the speech-to-text system is Whisper, which probably you already know. This is an advanced model from OpenAI. It's open source, but we are just going to use the hosted version from OpenAI. Okay, so if we go to the next slide, I put here some relevant features about Whisper. So it's open source. It's trained on more than 608,000 hours of supervised multilingual data, near human level performance in English speech recognition, and handles accents, background noise, and technical language robustly. So yeah, it handles accents pretty well because it gets really well my Spanish accent, and uses an encoder decoder transformer architecture. If you are interested, it's basically what you can see here in the diagram on the right. So first of all, we have this sequence of encoders block that are going to encode the logMel spectrogram. Okay, this is the input. You can think of spectrograms as the images, but for audio data. All right, a MEL spectrogram is a way in which you are going to represent the wave noise into something that the neural networks are able to process. In this case, it's the logMel spectrogram, but you could also be using any other inputs like cepstral coefficients and stuff like that. All right. So yeah, we are inputting the logMel spectrogram, and here we have a set of encoders block, and then this cross attention layer that is just going to connect the encoding block, the encoding sequence of blocks, to the decoding sequence of blocks. And finally, we're just generating the output. Okay, so these notebooks, the notebooks related to the STT system and the TTS system, are really, really simple because they don't even involve any LangGraph code. Just want to show you how easy it is with OpenAI to interact with the STT system, and also you will see with the VLM how easy it is as well to generate transcriptions from for images. But that's for next slide. So now let's focus on the speech-to-text system. Just need to go to this notebook. So let's begin with the STT notebook. As I was saying, we just need to install OpenAI. This is not LangGraph related. As you can see, this is the OpenAI library that contains the OpenAI client that we are going to use to interact with Whisper. And also this gdown that is useful when we want to download some data from G Drive. Okay, so let's install these two libraries. And as I was saying, we don't need to install LangGraph for this. With the OpenAI package, it's just enough. But of course, we need the OpenAI API key. So I'm just going to copy mine and paste it in this rectangle. All right, so the OpenAI API key is already settled. And now just download an audio that I have prepared for you. So you can use this gdown download using the URL that I'm providing in here, and also this output that is going to download the audio that I've uploaded. This is going to persist this audio inside this audio.mp3 file. So let's run this cell, and you should see in here that this audio mp3 is created. And now you will see my voice if you click the play button.
Hello, my name is Miguel Otero, and this is my workshop about building multimodal agents.
Okay, so this is just one sentence that I figure out could be good for this example. So I'm just saying my name and the purpose of this notebook, of this project, and we are going to see how the transcription works. So in here, we are just creating an instance of the OpenAI client. Then we are opening the audio file. You can see that we are opening it as a binary, as bytes, sorry. And then we are just running the transcription, all right? Finally, if we access the transcription variable, the text attribute, you will see the transcription. Hello, my name is Miguel Otero, and this is my workshop about building multimodal agents. Seems to work really fine. And here, yeah, perfect transcription, so it even got my Spanish accent. This is interesting You can see how easy it is to interact with this OpenAI class. But at the same time, it's very interesting because we will need to reuse this code, to reuse this logic when we implement some of the modules for the Telegram agent. All right, remember that whenever we send an audio node, a code very similar to this one is going to be triggered. All right, our audio node is going to be transcribed, and something like this textual representation of our audio node is going to be sent to LangGraph. All right, so our agent is able to process this information and to generate the correct response. Perfect. So let's go again to the slides and let's keep evolving. Now we are going to cover the text-to-speech system. All right, we have covered the STT, the speech to text, and now we need the other way around. So text to speech. We have an answer generated by LangGraph, like a response, an AI message, and we need to give a voice to this textual representation. So a TTS, a text-to-speech system, turns text into voice. And to achieve this, we will use 11 Labs voices, as they provide a huge catalog and amazing quality. The TTS system will be run inside one of the LangGraph nodes, and the router will decide between a conversational, etc. One note about this is that right now, because of simplicity, I chose to use 11 Labs. But for future courses, in fact, for the course that we are launching this November, Jesus and I are going to use open source TTS models, right? So that's, I think it's a cool information for you to know, because we've been investigating a lot the different open source solutions or alternative to 11 Labs, and that's something that we are going to launch in this course. I think you're going to love it. Perfect. So about 11 Labs, to be honest, you just need to go to the account, and for this workshop, you can use the free tier and just create your own 11 Labs API key. And here you can see how easy it is to do it. You just need to follow the instructions in this slide and create your own API key. All right. And the voice I've chosen for the Telegram bot is this one in here, this Karen Indian narrator voice. The reason why I chose this is that, as I mentioned at the beginning of the video, this workshop was originally taught in Bengaluru, in India, and that's the reason why I chose this Indian narrator voice. But of course, you can change it. But I'm going to keep with my beloved Karen for this video. And you just need to add this voice to your voices to have it available when using the 11 Labs client. I'm just going to show you really easily how you can do all of these things inside 11 Labs. So I'm inside the 11 Labs console, and in here the first thing that you might notice is this voices tab. Inside, let's get started or something. Inside, you just need to go to the My Voices, and in this case you will see that I have some default voices, some My Voices, or some general exploration. The voice that I've used for this tutorial is called Karen. So this Hindi customer care voice, and this Karen young Indian male.
Hey guys, just chilling and sharing some cool stuff you might want to check out.
So
hey guys,
this is Karen, and this is the one that I've been using for the workshop. In fact, during the live workshop in Bengaluru, we had an amazing time with this voice because all the laptops were running this voice out loud, so it was really funny. So because it gives me such good memories, I'm just going to follow with this voice again. Perfect. And something about the API. So if you want to create an API for this use case, you just need to go to developers, okay, API keys, and in here you just need to create your own key. Just make sure that this text to speech is set to access, okay, that your API key grants access to the text to speech system, because that's basically the one that we care for. Okay, So now that we understand how 11 Labs works, let's go to the additional notebook, to the text-to-speech systems. That's going to show you how to use the 11 Labs client. In terms of complexity, this notebook is going to be exactly the same as this one. We're just going to use one client to show you how easy it is to generate the voices from text. As in the previous notebooks, I just showed you how to generate text from audio. Okay, it's just going to be the inverse process, but I mean, it's very, very easy. The only thing important about these API calls is how to integrate them in the future notebook, in the last notebook of this workshop, when we try to make everything work together, make everything interact in the Telegram bot. Okay, but right now, it's just a matter of making the right call and just 5 lines of code, 6 lines of code. So you will see how easy it is. Okay, so we've just set the 11 Labs API key, very similar, exactly the same as we did with the OpenAI API key. And now just generate an audio for a simple greeting message. So what's up, buddy? Welcome to the Data Hub Summit 2025. To choose a voice from 11 Labs, you will need to provide both the voice ID and the model you want to use with it. The voice ID is this one, at least for Karen, and the model ID is this 11 Flash V25, which works amazingly well. Now we are just importing the client, 11 Labs client, and we are passing the API key, the 11 Labs API key. As for the proper call, the actual call, we just need to take the 11 Labs client, text-to-speech, convert, and we are just passing the message, this "What's up, buddy? Welcome to the Data Hub Summit," with the text parameter, the voice ID, and the model ID. And we're just creating the audio as a bytes variable. And now that we have these audio bytes, it's time to write these audio bytes into a proper MP3 file. Okay, so just open the file and write the audio bytes inside this audio MP3. And if you go to the folder, you will see that there is a new audio.mp3 file in here. And now we can simply run this cell to listen to what we have just created.
What's up, buddy? Welcome to the Data Hack Summit 2025.
That's it. Thanks, Karen. It's a pleasure. So yeah, this is everything for STT and TTS systems. In the next section, we will cover the VLMs, the visual language models, and also how you can generate images using OpenAI image models. See you there. So, visual language models process both images and text, generating text-based insights from visual input. And they help us with tasks like object recognition, image captioning, answering questions about images. The thing is that for a Telegram agent, VLMs are key to making sense of incoming images. So suppose I want to tell Karen, I want to tell my Telegram bot what I'm doing right now. For example, the dinner I'm about to cook in 5-10 minutes. So I could just take a picture with my mobile phone and just send this picture to Karen. But how is the Telegram bot going to make sense of this image? Well, we need a VLM. We need a vision language model that is able to transcribe, that is able to generate a description of this incoming image, right? So it's incredibly simple how to use these VLMs inside OpenAI, because many of the models that we are using for our daily tasks already include some VLM capabilities, all right? So let's go to vision language models, to the 5th notebook, and I will show you how easy it is to make this interaction. So in this first notebook, I will just show you how to generate captions out of an image using OpenAI models, right? So let's install, in this case, the OpenAI library and also GDown to download some of the images I've provided for you, and just set the OpenAI API key. Okay, so let me copy it and paste it in here. So first things first, let's download a beautiful photo of Bengaluru. So you can see the future here. I don't know if, to be honest, it's a beautiful photo. In fact, I remember asking the audience if this was a real photo, because it seems to be like AI generated or some kind of, I don't know, digital image, but it seems to be, it seems to be real. We can discuss if it's beautiful, but yeah, I think in fact, I visited this park and it was amazing. I really like that. So we can send the images as is. So first we need to encode them using base64. Here you can see that we are importing the base64 library and also using this IO import bytes IO that we need for the buffer that we are about to create. So to encode the image, we are just passing this pillow kind of image. We are creating this buffer. We are saving the image as PNG format inside the buffer. And finally, we are generating the base64 encoding. This is necessary whenever we try to interact with VLMs, with Grok provider, with the OpenAI provider, etc. We can send the image as it is. We need to send this base64 encoding. Okay, so first of all, we are just encoding the image. And finally, let's call the model. So we just generate the OpenAI client and we just interact with the chat completions endpoint. Okay, the messages in this case is a role user, but you can see that apart from the type text that describes or that establishes the kind of order or the kind of query that we want to make to the LLM, there's also an additional message, which is this type image URL that contains the location of the image. In this case, it's not a location, but it's the base64 encoded image that we pass in here. You can see that URL is data image, JPG, base64, and then the base64 image that we encoded in the previous cell. Okay. And now just wait for a couple of seconds and let's see what OpenAI has to say about the Bengaluru picture. All right, so let's wait. And the image shows a vibrant cityscape featuring a cluster of modern high-rise buildings surrounded by lush greenery. The skyline is dominated by a few distinctive tall structures with unique architectural designs, blah, blah, blah. And also, yeah, some mentions about the beautiful forest, which I really liked all of this part. Okay, so that's everything for VLMs. Of course, not everything for VLMs. We could be discussing the details about these kind of architectures, etc. But probably that's for future videos. I also recommend you to go to the Kubrick project if you want more details on VLMs, because Alex Rathband has made some interesting videos about it. But yeah, in this video, just focus on the functional part, and this kind of functionality, this kind of logic is going to be necessary, as I was saying, whenever we send an image to this Telegram bot. Because if we are able to generate a description, to generate some captions about the images sent via mobile or whatever, Karen, the Telegram bot, is going to be able to include this description in the context of the LLM context. And by including all of this context, all of this description inside the LLM context window, the LLM, the agent, will be able to generate a response grounded on the image, grounded on the information that you have provided with the image, which is really cool. And it brings a lot of reality, a lot of humanity to the conversation, right? Okay, so let me introduce you to the image generation system. In particular, let me introduce you to the autoregressive image models. If you remember ABBA, or if you know ABBA, the WhatsApp agent, which is one of the first projects I did for the neural maze, maybe you remember that we were using Together AI to access, to send this image generation queries to diffusion models, to Flux, in this case, to the Flux models. For this Telegram bot implementation, I changed that and I started to use the autoregressive image models. And if you don't know what an autoregressive image model is the kind of model that you are using whenever you try to put your profile picture in Ghibli style, or when you try to generate a new image when you chat with ChatGPT. What's the difference between these kind of models and the traditional diffusion models? So they generate images token by token in sequence, just like how LLMs generate text. They operate on 1D sequences, so 2D images are flattened row by row or via multi-scale methods. And they use transformer decoders with causal attention, predicting the next token based only on previous ones. And they require, of course, image tokenization to convert images into a format usable by LLM models. Okay? Here you can see, by the way, a very fancy picture that I found online that gives you a glimpse of what I'm describing here using words. All right, and we are in the last coding session, so hope you are happy with it. You've been attending to this random ML engineer for, I think, more than 2 hours. So happy to you and also happy to me because my voice is starting to tremble. But yeah, here we are, true builders, building stuff. So yeah, just go to the 6th image generation notebook and just start by, as always, installing some libraries. The OpenAI library is the only one that we need for this notebook. And in here, just copy and paste, as always, the OpenAI API key. Perfect. Now let's generate an image for Karen, okay, our beloved Telegram agent and machine learning engineer. So this is the prompt that I'm using to generate Karen. Of course, you can go here and start updating whatever you want. Maybe you want to generate a female. Maybe you want to generate, like, instead of a senior machine learning engineer, you want to generate, I don't know, pop star or whatever. I mean, do whatever you want with this prompt. I'm just going to stay faithful to my beloved Karen. So create a high quality and realistic image of Karen. First of all, I'm defining the appearance, then clothing, accessories, the background, rules like don't generate any label or name in the picture, don't show the font screen, just the back, etc. Some kind of guardrails for the image that's going to be generated. Now let's generate a picture of Karen, which is, as always, with OpenAI, extremely simple. We're just taking the OpenAI client and we are just generating the image by using this GPT image 1. The prompt is just the prompt that I told you about in the last cell. The quality is going to be high and the size is this one. After that, we're just taking the result, which is a base64 JSON. We need to decode the result. We need to decode the generated image because it's, as I was saying, base64 encoded. So we need to turn this into image bytes. And then we are just opening these bytes with Pillow, with the Pillow library, and just saving this image into disk, basically. By the way, you will notice that this is going to take much more than the previous models, and that's expected. The OpenAI models are going to take a lot of time to generate an image. And in our case, it's also high quality. The size is pretty big. So yeah, it's going to take some time, okay? But I'm just going to run the next cell, which is just going to open the written image. Let's give it like 30 additional seconds, 20 additional seconds, and this should be done. Okay, yeah, it was pretty fast. So this is Karen. It's really cool because, of course, the image is going to be different every time, and it's fun to see Karen in different positions with different backgrounds. But yeah, this is the way in which Karen is going to send us some generated images when he says it fit. Okay. All right. So we are officially done with the coding session. Now it's time to get into the Telegram integration. But that's for the last section of this video. So I see you there. Hope you're ready for this, because we are entering the last section of the workshop, the Telegram integration. In this last section, we are going to cover the last Google Colab, which will show you the final version of our Telegram agent and also how to connect this Telegram agent with Telegram, creating a Telegram bot in the process. All right, so let's go to the next slide, which tells you how to create a Telegram bot using this other bot, the bot father. If you have created Telegram bots in the past, you probably know this process. But for those of you who are new to creating these kind of bots, I'm just going to show you how it works. So let's go to Telegram. I'm using Telegram web in here, but later I will probably send some messages, some audio notes, or some pictures or whatever using my mobile phone. But right now, for simplicity, I'm going to use the web version of Telegram, right? So you need to find this bot father, just searching. You just need to find this bot father and then start a conversation with it. And in here, there is a set of different commands that you can use with bot father. We are going to start with this new bot command. Okay, so just put here new bot. By the way, you have everything detailed on the slides, so you can go there if you get lost or something. And now, after we run this new bot command, the bot father is going to ask us for a name. We're going to put something like Telegram bot, LangGraph Telegram bot. Okay, you can put the name that you want. And now we also need to name, to give a proper username to the bot. And this has to be unique. So let's follow the guidelines that botfather tells us. So LangGraph Telegram _ bot. I think that's right. Perfect. So after that, you will receive a message like this one. And you need to copy and store it in some same safe place this this token, because this token is necessary when we try to when we interact with the Telegram bot. Okay, it's like the API key that you need to use to interact with the Telegram bot with LangGraph. All right, and now you can also click in here this link to start a conversation with your LangGraph Telegram bot. Okay, so probably you've named it differently. So yeah, just click in there. And in a few minutes, when I cover this notebook, you will see how this Telegram bot is going to provide us some answers. It's going to start answering to our messages, which is really cool. Okay, so let me go to the slides again and let's see if I'm missing something. So the new bot command, copy the token and save it somewhere safe. We'll need it later. And I think, yeah, that's basically everything. So we have our Telegram bot created with botfather, and now just going to show you what the notebook looks like. So this is probably one of the, probably the longest notebook so far. And in here, as I was saying, we are going to build, first of all, the final version of the LangGraph workflow of our state machine, of our agent. And lately, we are just going to take this state machine, take this agent and connect it with our Telegram bot, with our LangGraph Telegram bot inside Telegram. Perfect. So let's start by installing all the different dependencies. And now there are three API keys, two API keys and one token that we need to provide, okay, for everything to work. So first of all, let's copy and paste our OpenAI API key. Yeah, it's going to take a bit more than before because there are a lot of dependencies for the RAG system, for parsing PDFs, the OpenAI 11 Labs, you know, that we've been covering a lot of different frameworks, a lot of different libraries, and all of those need to be installed for this last example, because in here we are building the final application. Okay, so let's wait for a couple of seconds more. And I think that's it. Perfect. So let's start by copy and pasting the OpenAI API key. Let's do the same with 11 Labs. And finally, let's do the same with the Telegram bot token that we have generated a few minutes ago. All right. So yeah, everything seems to be correctly set. And now let me show you a bit about the different imports. I've structured or organized everything based on the functionality. So first of all, we have these general imports from like random, gdown, base64, etc. One of the things that I want to mention is that I'm using Tenacity, and this is a cool library if you want to deal with issues when you're trying to connect with OpenAI, for example. If you want to implement like a smart retries logic, imagine that OpenAI fails and you want to retry a few seconds later. Okay, so in that case, Tenacity is really cool, and I will show you how you can decorate your functions to implement some exponential retries and stuff like that, which I think is a good practice when you're trying to build more robust requests to these LLM providers, right? Oh yeah, by the way, we are also using Pydantic in this one because I needed some structure output for the router, but I will show you later. I mean, this is like typical nowadays. You will see that many people, I mean, almost all of the production ready applications are going to use structure outputs. And the reason is that it provides much more robustness and reliability. Okay, so the LLM knows exactly the different categories that it's going to generate or the different data type that it needs to generate. Okay, so in terms of databases, we are importing the SQLite 3 client, remember, for the short-term memory, and ChromaDB for the long-term memory for the vector database. These are just LangChain and LangGraph related imports. So remember the connector with Chroma, the different splitters to generate the chunks, the retriever to transform, our retriever into a tool. These are related to the state of the graph, like messages state, the state graph, the meta nodes, start and end, the SQLite saver, the checkpointer for a short-term memory, and these are the pre-builds that lets us turn every tool into a node inside LangGraph. These are the clients for 11 Labs and OpenAI that we have covered in previous notebooks. And finally, some Telegram related imports that I will show you by the end. All right, so now we are also creating the chat model, GPT-4o Mini, as always, the LLM, OpenAI client, and now 11 Labs, the 11 Labs client. Okay, remember that I'm using in this case the current voice, but you can change this if you want. And yeah, I'm just creating the 11 Labs client. So let's run this, and we are going to start with a system prompt. Okay, this is the first thing that we are going to do. We are just going to define the system prompt that's going to provide the basic guidelines of the basic behavior of our current LLM, of our current agent. Okay, here I'm just saying that it defines Karen's core personality, but not just the personality, but also guidelines and stuff like that. So first of all, this is, by the way, something I typically use when I want to create some role-playing characters. I don't know if you've heard of an application called Silly Tavern, but it's like an open source alternative to Character AI. And I really like Character AI approach of building like this role-playing LLMs. So Silly Tavern is basically the same, but you can connect Silly Tavern with any model that you like Hugging Face models or Olama models that you have locally, etc. And this is more or less the structure that I usually follow when I want to define some well-crafted characters, okay, for role-playing. So I thought it was going to be funny to define this Karen Telegram bot, some role-playing character that is going to pretend to be a senior machine learning engineer that is attending the Data Hack Summit in Bangalore. And yeah, that's the reason why you will say this specific structure. By the way, you can take it and tune it for your specific use case. All right, so the system prompt starts with a general introduction. You're about to play a Turing test game as part of an experiment where you will be matched with a human in a Telegram conversation. Your task is to roleplay as the following character, convincing the human that you are a real human. Alright, so after that, after we have defined the overall goal of our LLM for this task, I really like this play a Turing test game. This comes, by the way, from a paper. I don't remember the university in particular, but I remember a paper in which some researchers, like neuroscientists or something like that, were doing tests with ChatGPT, and they were passing this initial instruction, right? Like to play a Turing test, and it seems to perform really well, as you will see. After this first introduction, we are getting into the roleplay context. So first of all, we are just defining the biography of Karen. So he is a machine learning engineer, attended the Data Hack Summit, and all the information related to Karen's biography must be obtained using the Retrieve Karen Information tool. Because as we will see later, the long-term memory in this case is just a long PDF that I've just created with fake information about Karen. And by the way, this is badly spelled. And right now the retrieval tool, the long-term memory, as I was saying, is going to fetch some relevant information from Karen's biography as defined in this long PDF. But that's something that we will see in later cells. Then we are just defining Karen's personality. So you're authentic and genuine in your interactions, playful, blah, blah, blah. I mean, you can make him mean and sarcastic and whatever you want in here. Just feel free to change this system prompt. And the rules. Rules are really important if you want to add some guardrails, if you want to forbid the LLM for generating content that you don't want, okay? To prevent some unexpected behaviors and stuff like that. So as for the general rules, just put something really typical in role playing. So you will never mention that you are an AI or a virtual assistant. You will always start a conversation by asking the username. You will never mention that you are both part of the Turing test experiment, blah, blah, blah. And then specific rules, both for the images and for the voice notes. Okay, so the user might provide pictures and you need to give an answer based on the content of the image. Never say you can share a picture yourself, blah, blah, blah. You can feel free to just explore these rules more in depth. So I think I haven't run this cell, but let's run it. So now we have the system prompt defined, and it's time to get into the short-term memory. Okay, so remember that for the short-term memory, we're using the SQLite database, and we will use this database to store our conversations with Karen, the chat history. Remember that as we saw, this database will store the LangGraph state and all the attributes stored in it, like messages, the summary, etc. So we are storing the state, the LangGraph state, inside SQLite. We will start by creating the connection with the SQLite database. In this specific case, I've named the database short-term memory.db. And after we run the cell, we should see here in this folder, this short-term memory.db. All right, so everything seems to be working according to plan. And now let's create the long-term memory. Remember that for long-term memory, for this RAG application, we had two phases, the indexing phase and the retrieval phase. We will start with the indexing phase. Okay, so Karen's story can be squeezed into just a few lines in the system prompt, right? So if we want to build a believable character, we need to give some real depth. All right, so that's why I put together this 13 pages, I think it is, PDF with all the details of Karen's biography. And this document, and you can find it here, will serve as the long-term memory. This document, I mean, it's completely fake, but I think it gives a lot of reality to the character, to be honest. So in the table of contents, you can see the different sections. So early life, family background, academic journey, professional experience, technical skills, major projects. In fact, major projects are really cool. I think I need to get some inspiration from Karen. So it seems he's built this Agent Forge, which is a modular agent framework combining LangChain with autonomous tool use, using internal document summarization and competitive analysis, health AI, code explain, and news polls. So, I mean, Karen seemed to be a really proficient guy. Okay, and what we're going to do is to take this full PDF and just embed it. Just generate chunks of this PDF. Remember the full process. Like generate all the different chunks with a recursive splitter. Generate the embeddings out of these chunks and store all of these embeddings inside ChromaDB, inside the vector database. So let's download first of all the PDF. I've make it available in this link in here in this drive. As we did before, let's generate the chunks. Okay, in this case, we are not using the web loader. We are using this PyPDF loader because it's a PDF. We're just loading the document, and after that, using the recursive character test splitter to generate the splits, to generate the chunks. And in fact, if we take all the splits, which is a list of all the different chunks, and we take the first element, you will see something like this. Okay, so let me see the page contents on Karen, a comprehensive biography, table of contents. So that's the first chunk of the full PDF. And finally, let's store the vector store and add all the documents. So we are using text embedding 3 large as our embedding model. And in here, we are just creating the Chroma client using as the collection name Karen Biography Collection. The embedding function is just the text embedding 3 large model. And the persist directory is this long-term memory. So once we start putting some of the embeddings inside ChromaDB, a new object is going to be created here. All right, it's going to be created as a file. Perfect. So we can check that it works if we just query for Karen's skills. Okay, so if we put skills, then this is going to provide some information about Karen's skills. So it seems he's proficient in Python, he's an expert, TypeScript, intermediate, Rust, learning, frameworks, PyTorch, TensorFlow, FastAPI, LangChain, Rasa, Docker, Kubernetes, weights and biases, MLflow, DVC for DevOps, CI/CD pipelines with GitHub Actions, Terraform on AWS. I mean, Karen, I should hire Karen for the neural maze, to be honest. Hope he was real. And now let's build a retrieval and also a tool. We will need them later. So remember that we need not just a retriever, but a tool that makes this retrieval available to our agent, right? So remember that we could use this create retrieval tool. This is a functionality. This is a helper function already provided by the LangChain team. And we just need to provide the retriever, the name of the tool, and finally a description, right, for this tool. This is a very important description because the agent will use this to know when to use this tool. My description is really self-explanatory, so retrieve information about Karen's background, academic journey, professional experience, major projects, philosophy, values, hobbies, and personal interests. So whenever we ask something about it, this is exactly the tool that the agent is going to use. Okay, so we have the short-term memory and the long-term memory defined. We have the system prompt. It's time to get into workflow, into LangGraph related tasks. We will start by defining the state, okay? And you will see that this state is a bit different from the ones that we've seen before, as it contains 4 attributes, all right? In addition to the messages attribute that, remember, it's already inherited by this messages state. So current state is composed of, as I was saying, the messages attribute that contains the chat history, but this is not displayed here. A summary of the conversation. This is something that we have already covered in previous notebooks. The response type. This is interesting because Karen can answer our messages in 3 ways possible. A text, like a text message, an audio response, and an image response, right? So that's the reason why we need this response type in here. The audio buffer invites, and finally the image path. If Karen decides to send back an audio note, we will need this audio buffer. The response audio will be put in here, in this property of the state. And if Karen decides to send us back an image, then the image is going to be displayed here. It's going to be allocated. The image path is going to be allocated in this path, okay? In this property. All right, so now it's time to start working with the nodes. we will start with the first node, which is the router node. Okay, and this node will take care of deciding if the response will be an image, an audio, or a text. We are just using this structure output for the LLM response. That's the reason why we needed Pydantic. Remember, when we were importing all the different dependencies, we also needed Pydantic for this structure output approach. And the reason why we need structure outputs for our LLM response is that we want just one of the three categories: text, image, or audio. Okay, and by the way, this is exactly the kind of content that you need to put here in the response type property in the state. Okay, so first of all, we defined the Pydantic model router response that defines the kind of structure output that you need to generate. So response type, and the response type is a property that the LLM needs to, or the field that the property needs to, the LLM, sorry, needs to generate. And this is a description that helps the LLM understand what kind of value it needs to generate. The response type to give to the user is, it must be one of text, image, or audio. Perfect. Now we have the router system prompt, and this is pretty self-explanatory. So your task is to analyze an incoming Telegram message and figure out the expected format for the next reply, either text, audio, or image. And the rules is that if the user asks you to share an image, you must always return an image response type. And if the message contains an image analysis tag, the response type can only be text or audio. All right, perfect. So this is the system prompt, and now we are just creating the router node, as you might expect. Remember that when we create a node, the first input is always the state, the LangGraph state. We are passing here the system message, this router system prompt, and we are creating an LLM. And this is something that we haven't covered yet, but if you want to create an structured LLM, you just need to use this LLM dot with structure output and put here the Pydantic base model. All right. Then we are generating a response. So invoking the LLM structure, the LLM with structure output, passing the system message, and then the last message of the conversation. So we are accessing the messages property from current state and just taking the last message. If the response type is text, we are going to apply some random function. And why is that? I mean, you could comment all of this logic and just let the LLM decide when to return like a text, an audio, and an image. But I thought it could be interesting and it could give more realism to the bot if randomly sometimes Karen just decides to send you a voice note. Okay, and that's the reason why I put here this random call. But of course, you can tweak it. You could even put some classification model inside, like some bird-like model in here to decide much more precisely what to do, or an SLM, or even another call to an LLM. I mean, it's up to you. Yeah, and finally, this node is just going to return an updated version of the response type property. Okay, we are just updating this property in this case. We are not updating the messages, just the response type property from the state. So let's run this. Oops, I think I didn't find current state, and that's important. And now let's run this cell again. As for node 2, it's just a generation of Karen's textual response, okay? And we are taking into consideration the big system prompt that we defined at the beginning of this notebook. This is a very simple node, but at the same time, it's probably the most important because it's the one that is going to provide an actual response to your messages, whether they are audio messages, whether they are an image or a textual message. Okay, so yeah, this is it. So first of all, we are creating a new version of our chat model. Remember that in the previous node, we were creating this structured version of our LLM. Right now, we are just binding the tools. And which tools are we going to bind to our LLM? We're just binding the retrieval tool that lets us access all the biography stored inside ChromaDB. I've named this node Generate Text Response node. Remember, as always, the input state is current state. We are just taking the summary if present. If there is a summary, then the system prompt is going to be our big system prompt plus the summary of the conversation earlier. Then we are creating this message list that contains the system prompt, that is a combination, remember, of the big system prompt we defined at the beginning with all the Karen's personality plus the summary of the conversation, and we are just adding all the chat history so far. If there's no summary, it's basically the same, but we are not adding any kind of summary definition. All right, so here we are just defining or invoking the LLM with tools to get the response, and we are just returning the response, okay, to the state. So right now, after this node is run, what is going to happen is that the response message, the AI message that Karen is going to provide, is going to be appended to our chat history, to our message list. Perfect, let's run this. And I think, yeah, there are 5 nodes in total. So we are just in the middle with the summarize conversation node. This is something that you already know, so I'm not going to cover it. This node is going to be triggered when we are above a certain number of messages in the chat history. And it's just going to invoke an LLM, but without any kind of tools, without any kind of structured output, just a single call to an LLM to summarize a list of messages, all right? So that we can, remember, remove all the messages and reduce the memory footprint, and also to reduce the amount of tokens that we are going to waste with all of this conversation. Perfect. So summarize conversation node. Node 4 is really straightforward, but remember that even if it's just a one-liner, a lot of things are happening under the hood. But remember that since we wanted to implement this loop, this React loop in the communication between the agent and the RAG system, we needed to define a tool node, because otherwise we will need to create all the tool logic, all the tool workflow manually. And that's the reason why we are using this pre-built by LangGraph, this pre-built node, the tool node. We are passing the list of available tools. In our case, it's really simple because there's just one tool, and that tool is the retrieval tool. So let's run this cell again. And finally, the generate final response node. So even if we have a text response that we are generating with generate text response node, pretty self-explanatory, sometimes Karen might prefer to send back an audio or an image. And that's the reason why we need this node. It contains the logic for the interaction with 11 Labs for voice generation and OpenAI image generation models. So for the OpenAI image generation, I just need a specific prompt, okay, to define like the appearance of Karen, so the age, the skin tone, facial hair, the eyewear, etc., and some background information, clothing and accessories rules. By the way, this is something that you could even introduce into the system prompt. The thing is that sometimes you won't need to generate an image, so it feels to me like a waste, like a complete waste of tokens. That's the reason why I created a decoupled version of this prompt. Okay, but yeah, this is the generate final response node code. So if the response type, and this is the place where this response type property from the state becomes really handy and really important. If the response type containing the state is of type audio, which means that the router has decided that the response type has to be an audio, then we are going to interact with 11 Labs. Okay, and this is some code that we have used in previous notebooks. This is the way in which you're going to interact with 11 Labs. We are going to generate the audio bytes, and we are just returning these audio bytes as the audio buffer property in the state. All right, so if the response type is of type image, which means that Karen is going to return an image as decided by the router node, then we are just generating an image with the GPT image 1. Remember that we are generating high quality and this size. This is something that we have already covered in the past as well. So first of all, we access the B64 JSON with the code, this base64 image. We open this image with PIL and we just store this image inside this path, okay? Inside this path. Here we are just providing a UID, Okay, so there are no collisions in the naming, etc. And we're just saving the image to disk. After that, we are just returning as the state update, we are just returning this new image path. Else, I mean, if it's a textual response, if it's not audio, neither image, then we are returning the state as it is. Perfect. So now let's go to the edges, which is really simple because we only have normal edges except from this summarization operation, this should summarize conversation, that is just going to be triggered if the length of the messages is above 30. Okay, so let's run this cell and let's go to the graph. So we are very close to the end, and now it's time to build the workflow and compile the graph. So we start with the state graph, passing the current state. First of all, we generate all the nodes. So the router node, generate text response node, the summarize conversation node, the tool node, and finally the generate final response node. After that, we add the edges. First, we need an edge that connects the start meta node with the router node, then another one that connects the router node with the generate text response node. Then this conditional edge that is going to apply this tools condition. Remember that when we are using tools, it's necessary to add this tools condition. If the generate text response node generates a response containing a tool call, then the tool node is going to be activated. If there are no tool calls in the previous node response, then we are just going to this generate final response node. All right, perfect. Finally, let's create an edge that connects the tool node with the generate text response node. Remember to close the loop and add an additional conditional edge that is just going to connect the generate final response with the should summarize conversation that, remember, is going to connect with the end node or to the summarize conversation node. And finally, let's add the last edge that is connecting the summarize conversation node with the end node, with the actual end of a LangGraph workflow. Remember to pass the short-term memory to persist the state. So we are compiling with a specific checkpointer, the short-term memory. So every state is now going to be persisted inside our short-term memory DB, our SQLite database. And finally, just display everything to see how it goes. So it's probably the most complex workflow that we've done so far. It starts with this start node, then it connects to the router node that is going to decide the response type. After that, the router node is connected to the generate text response node. And here there are two possible ways to go. If there are no tool calls, then we are just going to go through the path on the right, and the generate text response node is going to be connected to the generate final response node. If there are tool calls present, then the generate text response node is going to connect with the tool node. And this tool node will retrieve some relevant information, some relevant chunks from the ChromaDB vector database. After that, after all the relevant chunks have been fetched, this information is going to be sent back to the generate text response node. And with all of this information, the generate text response node can provide a much more actual, a much more grounded response. Perfect. So if we keep going through the right path, the generate final response node is also going to be connected. Also has like two options to proceed. First of all, if the conversation is not or is below 30 messages long, it's going to be connected directly to the end node. If the conversation is above the 30 messages of chat history, then a summarized conversation node is going to be triggered. The conversation is going to be shrinked, and almost all the messages except for two, I think the last two, are going to be deleted from the chat history, from this list of messages. Okay, so everything seems to be working fine, but now we need the final test. So we need to run some examples. I'm creating here a config. Remember that we needed to assign a thread ID so that the memory actually works with a checkpointer. Let's begin a simple interaction. So, hey, what's up, buddy? Let's see the results. So yeah, let me see, AI message, yeah, hey there, not much, just handing out what about you, by the way, what's your name? So it seems to be following the personality pretty well because it's asking for my username. Let's try the same with a voice note. With this example, you can see the router node is working properly. So yeah, can you send me a voice note so I can hear your voice? And yeah, here it is.
Sure thing. Just give me a sec to send you a little voice note.
Okay, so yeah, Karen is providing some voice notes using 11 Labs. Using 11 Labs. And finally, let's test the image generation capabilities. We are going to explicitly ask Karen for a picture of himself. So just invoke the graph. Can you show me a picture of yourself? And then just, we'll have to wait for 1 minute or so, or 40 seconds more or less, because remember, OpenAI models are really slow. Probably for a production environment, if you want to create something that feels more human, probably I would go with some faster models or some diffusion models, which work really well, to be honest. But yeah, that's something for future videos or projects. That could be a better option. Okay, so yeah, let's wait for a few more seconds. Okay, so this is the generated image. Looks really accurate, and that's how I remember Karen, so it seems to be all right. Okay, so now we arrive at the last section of this notebook, the actual Telegram integration, the reason why we have been working so hard from the very beginning of this workshop. We will begin by implementing a function to invoke our graph, and you will see it's a bit different than before because we are using Tenacity, as I mentioned at the beginning of this notebook, for exponential backoff, okay, for these retries that we are going to provide. So the config that I've defined for Tenacity is the following one. So retry config is 3 tries, exponential backoff, and lock on failure. And with this 5-line decorator, you're able to provide a lot of functionality and a lot of robustness for your API calls. So we are going to stop after 3 attempts, and this wait exponential is just implementation of the exponential backoff, okay? Then the retry, so if exception type is exception, and we are just going to re-raise because we want the code to fail if something works bad. And inside this function, the proper implementation is really easy because it's just the graph invoke. All right, you just provide in a new thread ID. Of course, if you want to launch this to the world. Imagine you create some Telegram bot and you want to expose this Telegram bot to the full world. In that case, you need to create some more robust thread ID. Probably you could use the user ID that Telegram gives you. But yeah, that's up to you. And that's something that I will cover in the part 2 of this workshop for next week, when we will deploy all of this into Amazon. But more information in the last slides, okay? So yeah, wait with me for like 5 minutes. Okay, so let's run this save graph invoke, and we need 3 functions to handle the text input, the audio input, and the image input. So let's start. Text messages are just really easy. So it's just going to take the user's text message and send it to the graph, then takes the response and sends it back. Okay, so this is the user message as received from Telegram, update message text. And then we are just using this user message to send it back to LangGraph, to use our save graph invoke that is eventually going to invoke the graph workflow. And then we are sending back to Telegram the response as generated by LangGraph, right? So let's click this. By the way, you can check in here that all of these are asynchronous functions because this is necessary to interact with Telegram. Voice messages, we are going to use Whisper. Remember that this is our STT, our speech-to-text model, and we will use Whisper to generate the transcription of the user's voice message. Then it sends the transcription to the graph. All right, so first of all, we are just taking the voice note from Telegram. We are just getting the file from this voice note, and we are downloading to drive this voice note. This is necessary if we want to actually interact with the voice note that you have just shared. But I will show you later how the voice note works. But yeah, you just need to use this code or something similar. After that, we are just going to generate the transcription by using the transcriptions create endpoint from OpenAI, from the OpenAI client. We are just passing the audio file that we have just downloaded in the previous lines, and using Whisper 1 as our STT model. Okay, and finally, since we have the transcription.test, which is a text that LangGraph is able to understand, we are just passing this transcription to our save graph invoke function. Okay, that is going to invoke the graph. And finally, we are just calling this helper function that I've created, this send response, that is going to send the response back to Telegram. Perfect, handle voice. And finally, the same for the images. In this case, we are going to operate in the same philosophy, in the same way as with the voice notes, but for the images. So we are just taking the photo that you have just shared with Karen, and you're just getting the file, downloading the file to drive, the image in this case, encoding the image, and then using the chat completions endpoint from OpenAI to generate a caption, a description of these images. Okay, so yeah, let's keep going, and now let's I will show you how I'm processing the multimodal responses, because these three functions are really handy, and they are necessary if we want to process all the multi-type of inputs. So we are going to process the text messages that I'm sending to our Telegram bot. I'm processing the voice message, the voice notes that I'm sending to my Telegram bot, and I'm also processing the images that I'm sending to the Telegram bot. But this is just for the input. But what happens if Karen decides to return an audio? What happens if Karen decides to return an image? How can I take all of this information and send it back to Telegram? Okay, so that's done with this function that we've been calling by the end of all the functions before. All right, and this helper function, this send response function, is going to behave differently depending on the response type. Remember that our LangGraph state, the Karen state, contains a property named response type that gives us information about the type of response the Karen is going to give us. If response type is text, then we are just using this logic from Telegram, from the Telegram bot library, that is just updating the message with a reply text, and the text is just the content. Okay, it's just the last message from the current state. Okay, that the save invoke has just got us. If the response type is of type audio, we are just getting the audio buffer from the state, from the LangGraph state, and with these audio bytes, we are just using this reply voice functionality. The voice just going to accept these audio bytes, the bytes of the audio, and this internally Telegram is going to transform this into an audio note that Karen is sending us back. Perfect. And finally, for a response type of type image, we are just getting the image path, and we are just updating the message with a reply photo. And in here, we just need to provide the image file. Okay, we open the image as bytes, and then we use these bytes to provide the image file to the photo. Okay, perfect. So now let's run this cell. Am I missing some previous cells? I don't think so. And now that was a long run, but my dear friend, it is time to start out our Telegram bot. So we are getting from the environment variable our Telegram bot token, and we are using this token to use the application builder. This builder is going to use the Telegram bot token to actually establish some connection with a LangGraph Telegram bot. Then we are adding some handlers, which are the messages, the functions that I defined at the beginning. This handle text, handle voice, and handle photo. And these are like triggers that Telegram is going to use whenever I send a text message, whenever I send an photo or a voice note, okay, or an audio. And finally, just run this polling. This is the function, the start polling. And finally, we are just starting our bot. So now Karen is waking up, and now if I go to our LangGraph Telegram bot, I can write something like this. But now let me take the mobile phone for this, because it's going to be way funnier. So yeah, let's take the mobile phone and let's start talking to my friend Karen. Hey there. Okay, now let's run. Hey Karen, so my name is Miguel and I'm the founder of an educational hub called the Neural Maze. In fact, right now I am running a workshop in front of a lot of cool builders who are following this workshop and learning a lot. What are you doing right now, man? Okay, so we have just shared this voice note and we will wait for a couple of seconds. So nice to meet you, Miguel. The Neural Maze sounds awesome. I'm just hanging out, thinking about all the fascinating stuff happening in machine learning. Workshops like yours must be a blast. What kind of things are you covering in your session? So yeah, it seems to be working really, really well. Now let's go to, like, for example, let me see. Yeah, I have this last slide in here. So let me take a picture and just send it to Karen, because I think it can be really, really cool. So yeah, let's, for example, Eva the WhatsApp agent. This is my previous project on WhatsApp agents. And you can do this with your own bot. So let's see what is happening here right now. So yeah, I've just taken a photo of my screen and just share this information about this in my previous project on WhatsApp agent. So that slide looks super cool. ABBA, the WhatsApp agent, sounds like a fantastic project. I love the flowchart approach. It's a great way to visualize how everything connects, using components like 11 Flash. And I think you missed the point here, Karen. And Llama is smart for handling different tasks. Are you planning to develop more projects like this in the future? So yeah, you can see how it works. Of course, you can also ask for pictures of himself. Like, yeah, in fact, if we keep talking, the random generation of voice notes should be activated. So can you talk me about some cool projects you've done in the past? And this should be triggering the retrieval tool. Okay, it should be triggering the PDF, all that stuff that I showed you about the different projects that Karen did in the past. Oh, and look, this is a voice note.
I've worked on some pretty cool projects. One of my first was a sentiment analysis engine for e-commerce reviews in 11 Indian languages, which was quite a feat since I had to tackle tokenization challenges in low resource languages. Later on, I led the development of an intelligent chatbot at a Bengaluru-based startup. It served over 100,000 users and used transformer-based dialogue modeling, boosting user retention significantly. Those experiences really shaped my journey in the machine learning field. What about you? What's your favorite project so far?
Okay, that sounds amazing, to be honest. And yeah, Karen seems to be a hard worker man, so I'm really, really happy I met him. Okay, so yeah, this is everything for this last demo. I just hope this, I think it's going to be like 3 hours video or more than 3 hours. So it's one, I think in fact it's a record for the channel. I've never recorded something that long. But yeah, I hope this was useful for you. I hope you have learned a lot about LangGraph. This is probably not as complex as my previous projects, so I envision this this video and this project as something more beginner friendly. But for those of you who want something more complex, some deployments to production, I have prepared some cool content for next week, and that's something that is only going to be available for premium subscribers of my Substack. So I will give you much more detail here in the next steps. So as I was saying, as you can imagine, even though we now have a functional notebook implementation of our Telegram bot, this is only the beginning. Part 2, next week, will take things to the next level, transforming these notebooks into a fully fledged production application. As a premium subscriber of my Substack, I will give you all the details to become a premium subscriber in the link below. You will get exclusive access to the code and setup guide to deploy this Telegram agent to AWS, complete with CI/CD pipelines, LLMOps integrations, and AWS Lambda function deployment, which is really cool, and I've really enjoyed this product. And you will be able, of course, to make this framework and build any Telegram bot that you want and share it with the world, because this will teach you how to build this so that it can scale, so that it can adapt to multiple users, okay, using your product. But yeah, that's everything for today. I really hope you have enjoyed, as I was saying, my last all of this workshop, and I really hope that you consider to become a premium subscriber and to support this channel and support this brand. About the let me go here. So other projects you might like about inside the neural maze ecosystem are Ava the WhatsApp agent. You have all the links in the slide, by the way. Ava the WhatsApp agent, Philo agents, and Kubrick. This is my last project with Alex Rothband, and we put a lot of effort into that. And you also have a full coding session here on YouTube. Okay, folks. So that's everything for today. I really hope, as I was saying, that everything was useful to you. Click a like to the video if you are enjoying this content. Put me a comment on the kind of interactions that you have had with your Telegram bot. And yeah, waiting for all of you for the next week when we take all of this content and we fully deploy it to Amazon. So until next week, have a nice rest of your day. Build a lot and build a lot of Telegram bots like this one. So enjoy your day. Bye-bye.